Hello there and welcome to Science for Sleep. Where curiosity gets cozy, the universe lowers its voice a little, and science takes the scenic route through the dark. Tonight, we're not going to a distant galaxy, or falling into a black hole, or standing on some stormy alien planet where the weather report includes molten metal and very poor umbrella options. Tonight, we are staying right here with the sun, the planets, the moons, the comets, the dust, the distant icy bodies, and this little Earth where you may be resting now. But the strange thing is, even when we stay here, we're still moving. The solar system is not parked in space like a lantern hanging quietly in an empty room. It is travelling. It is crossing the Milky Way. It is carrying us through a very thin, very faint region of interstellar material called the Local Interstellar Cloud, sometimes called the local fluff, which sounds less like a serious astronomical structure and more like something you might find under a sofa if the sofa had been floating between the stars for several million years. Before we drift into that invisible cloud together, let me ask you something simple. Where are you listening from tonight? Are you tucked away in a city, with streetlights outside the window and the soft hum of evening still lingering somewhere beyond the glass? Are you somewhere quiet, where the night feels wide and the sky has room to breathe? And what time is it for you right now, in your own small corner of this moving planet? It is a lovely thing to think about because wherever you are, and whatever time your clock happens to show, you are not still. Your room is moving with Earth as it spins. Earth is moving around the sun. The sun is moving around the centre of the Milky Way, and the whole solar system, with all its familiar planets and distant frozen edges, is passing through a thin local cloud of gas and dust that most of us never notice at all. If you find this kind of journey soothing, if you enjoy letting the big questions become gentle enough for bedtime, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of the internet reach other tired travellers who might also enjoy learning something quiet before sleep. And if you're already settled under a blanket, half awake and half ready to drift off, then you're in exactly the right state of mind for tonight's topic. Because the place we are moving through right now is not loud or dramatic. It does not flash across the sky. It does not announce itself with thunder or fire. It is almost unimaginably thin, quieter than any fog on Earth, thinner than the best vacuum we can make in many laboratories, and yet it is real. It is around us. It is touching the outer boundary of the sun's influence. It is part of the environment our solar system is sailing through at this very moment. When people think of space, they often imagine emptiness, a black background, a silent gap, a kind of nothing between the shining things. Stars over here, planets over there, galaxies far away, and between them, just empty darkness. And to be fair, space is mostly empty. If you are hoping for something cozy and crowded between the stars, the universe may disappoint you a little. But empty does not mean completely blank. The space between stars contains atoms, ions, dust grains, magnetic fields, cosmic rays, and the leftovers of ancient stellar lives. It contains material that has been blown out of stars, swept up by explosions, stirred by gravity, heated by radiation, cooled in shadow, and carried around the galaxy for immense stretches of time. Interstellar space is not a perfect vacuum. It is more like an extremely faint atmosphere spread across distances so large that our minds have trouble holding them in place. And right now, the solar system is moving through one small part of that interstellar environment. The Local Interstellar Cloud is a warm, partly ionized cloud of gas surrounding the sun's neighborhood. Warm in astronomy can mean something different than warm in your kitchen. This cloud is thousands of degrees in temperature, but because it is so thin, it would not feel hot in the ordinary way. Temperature measures the motion of particles, and those particles may be moving quickly, but there are so few of them that there is not much heat to transfer. It is a bit like being told that a nearly empty room is technically full of energetic dancers, and then discovering there are only 3 dancers in a cathedral. They may be dancing with great enthusiasm, but they are not going to warm the building very much. This cloud is not a cloud like the ones we see on Earth. It is not white and soft. It does not roll over the sun like mist over a field. It is not thick enough to hide stars from view. If you could somehow step outside the heliosphere and look around, you would not see walls of fog. You would not see the solar system wrapped in a glowing cocoon. The local interstellar cloud is far too thin for that. It is made mostly of hydrogen and helium, with traces of heavier elements and dust. Some of its atoms are neutral, meaning they have their electrons. Others are ionized, meaning they have lost electrons and now behave as charged particles. There is magnetism threaded through it too, because interstellar space is not just a place of drifting atoms. It is also a place of fields, currents, pressures, and slow invisible motion. The sun does not move through this cloud naked and unprotected. Around the sun is the heliosphere, a vast bubble inflated by the solar wind. The solar wind is a stream of charged particles flowing outward from the sun in every direction. It passes Earth, sweeps beyond Mars, Jupiter, Saturn, Uranus, Neptune, and continues far past the planets. Eventually, far beyond the orbit of Pluto, this outward flow slows and meets the pressure of interstellar space. That meeting place is not a hard shell, not a glass wall, not a clean border with a neat little sign saying, "You're now leaving the solar system, please check your pockets for loose moons." It is a changing boundary, shaped by the sun's activity, the interstellar magnetic field, the surrounding gas, and the motion of the solar system through the galaxy. The heliosphere matters because it is one of the reasons Earth has remained such a sheltered place. It does not block everything. Space is never that tidy. But it helps reduce the number of high-energy particles from the galaxy that can reach the inner solar system. It is like a protective weather system created by the sun itself. Not perfect, not permanent, not solid, but important. It stretches around us as we move, and at its outer edge, the solar wind meets the material of the local interstellar cloud. So when we ask what the solar system is moving through right now, we're also asking what presses on the outside of our solar bubble. We're asking what kind of interstellar weather is flowing past the sun. We're asking what the galaxy feels like just beyond our front garden. For most of human history, this was not something anyone could measure directly. Ancient skywatchers could track the sun, the moon, the planets, and the stars. They could map constellations, predict eclipses, and build calendars from the patient motion of the heavens. But the thin gas between the stars was beyond them. It does not shine brightly enough for the eye. It does not form shapes that appear in ordinary night skies. It does not behave like the clouds that gather before rain. To discover it, astronomers had to learn to read starlight carefully. When light from nearby stars passes through interstellar gas, certain atoms leave tiny fingerprints in that light. They absorb very specific wavelengths, narrow dark marks in the spectrum, like delicate clues left by material too faint to see directly. By studying these absorption lines, scientists can learn what lies between us and nearby stars. They can work out the speed, temperature, and composition of gas in our local galactic neighbourhood. That is how the quiet surroundings of the sun began to come into view. Not as a picture, exactly, but as a set of measurements, lines in spectra, signals from spacecraft, particles arriving from the edge of the heliosphere. The picture that emerged is both simple and strange. The sun is inside a larger low-density region called the local bubble, a cavity in the interstellar medium that was probably shaped by ancient supernova explosions. Within this larger bubble are smaller clouds and flows of warmer material. The local interstellar cloud is one of these nearby clouds, and the solar system is either inside it or close to a region where it blends and interacts with neighbouring cloud material. That uncertainty is part of the story. We're not sailing through a neat cosmic box with sharp edges. We are moving through a messy local neighbourhood where clouds can overlap, mix, shear, and drift past one another. It may feel odd that scientists can know so much and still leave room for uncertainty, but that is often how real science works. The universe rarely hands us a labeled diagram. It gives us hints. A neutral helium atom arriving from interstellar space, a magnetic field measured by Voyager, a pattern of energetic neutral atoms detected by IBEX, a slight absorption line in the light of a nearby star. Each clue is like one page from a very large book, and some of the pages are smudged, and a few may have been borrowed by another branch of physics and not returned on time. So astronomers compare models, they test possibilities, they ask whether the Sun is clearly inside the Local Interstellar Cloud, or whether we are in a transition zone between the Local Interstellar Cloud and another nearby flow sometimes called the G Cloud. The answer is not as simple as pointing and saying, here is the edge. Interstellar clouds are not made with tidy borders, they are more like currents in an ocean. This is one of the reasons tonight's topic is so gentle and so strange at the same time. We are moving through something real, but we do not feel it. We do not wake up in the morning and notice that the Local Interstellar Cloud has left dew on the windows. Birds do not change their songs, because the sun has drifted a little farther through interstellar gas. Your tea does not taste faintly of helium. And yet, on the scale of the heliosphere, this motion matters. The outer bubble of the sun is shaped by the pressure outside it. The number of cosmic rays entering the solar system can be influenced by the strength and size of that bubble. The stream of neutral atoms drifting in from interstellar space can be sampled and studied. The boundary of our solar home is not fixed. It breathes, shifts, and responds. Think of the solar system as a small boat moving through a very wide, very calm sea. Inside the boat are all the things we know best. Earth, with its weather and oceans, Mars with its rust-coloured dust, Jupiter with its storms, Saturn with its rings, and all the smaller bodies that fill the dark spaces between and beyond. Around the boat is a bubble of wind from the sun, like a protective envelope. Outside that envelope is the interstellar sea. It is not water, it is not dense, it is not something that splashes, but it has motion and pressure. It has direction. It has its own quiet conditions. And as the sun moves through it, the heliosphere forms something like a front edge, sometimes compared to the bow wave of a ship. Not a crashing wave, not a dramatic spray, but a subtle response where one moving environment meets another. The speeds involved are difficult to picture because everything in space is moving. Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the centre of the Milky Way at hundreds of kilometers per second. Nearby clouds of interstellar gas have their own motions too. There is no single, unmoving stage against which all of this can be measured. Still, relative to the local interstellar material, the Sun has a motion, and that motion shapes the way particles enter the heliosphere. It gives the solar system a kind of upstream and downstream direction, a nose and a tail, though the true shape of the heliosphere is still studied and debated. For a long time, people pictured it like a comet, with a rounded front and a long trailing tail. Later measurements suggested the structure may be more bubble-like, more complex, shaped by magnetic fields and particle pressures in ways that resist simple cartoons. The universe is very good at refusing to look exactly like the first drawing in a textbook. One of the most beautiful parts of this story is that some of our best clues come from spacecraft that were never originally built for this purpose. Voyager 1 and Voyager 2 launched in 1977 to explore the outer planets. They visited Jupiter and Saturn, and Voyager 2 went on to Uranus and Neptune. Their early mission gave us some of the most famous planetary images ever taken. But after the grand tour, they kept going. Decade after decade, they travelled outward, farther from the Sun toward the boundary where the solar wind gives way to interstellar space. Voyager 1 crossed the heliopause in 2012, and Voyager 2 crossed it in 2018. That does not mean they left the solar system in every possible sense, because the Sun's distant comets in the Oort cloud extend much farther. but they did leave the heliosphere, the region dominated by the solar wind. They entered the space between stars and began sending back direct measurements from beyond the sun's bubble. Imagine that for a moment. A human-made spacecraft built in the 1970s, still whispering home from the dark, measuring particles and magnetic fields in a region no human eye has seen. It is almost funny in the most wonderful way. The same species that misplaces keys while holding them built a machine that crossed the boundary into interstellar space and kept reporting back. The Voyagers do not give us a full map because they are only two travellers moving along two paths, but their measurements are precious because they are direct. They tell us what the outer boundary is like along those routes. They help scientists compare the inside of the heliosphere with the outside. They show how the sun's influence fades and the interstellar environment becomes dominant. Closer to Earth, IBEX, the Interstellar Boundary Explorer, has helped create broader maps of the heliosphere's edge. It does not fly out to the boundary itself. Instead, it detects energetic neutral atoms, particles that can travel inward from the outer heliosphere and carry information about interactions happening far away. This is a clever method, a little like learning about a distant shoreline by catching messages in bottles, except the bottles are atoms and the ocean is a vast region of plasma and magnetic fields. IBEX revealed surprising structures, including a bright ribbon of energetic neutral atoms that scientists did not expect before the mission. That ribbon became a clue that the interstellar magnetic field outside the heliosphere was playing a major role in shaping what happens at the boundary. All of these measurements bring us back to the quiet fact at the centre of tonight's journey. The solar system has an environment, not just inside, among planets and solar wind, but outside too. We are not isolated from the galaxy. The sun is a star moving through a neighbourhood. That neighbourhood has gas, dust, fields and history. Some of the atoms outside the heliosphere may have been forged or stirred by stars that died long before the sun was born. Some dust grains may have crossed unimaginable distances before approaching our solar bubble. The Local Interstellar Cloud is not just empty space with a name attached. It is part of the recycled material of the Milky Way. It is one faint passage in the long circulation of matter through stars, clouds, explosions and new generations of worlds. And this can change how we picture home. Home is not just Earth. It is not only the solar system as a set of planets orbiting a yellow star. Home also includes the motion of that star through the galaxy. It includes the bubble the sun makes around itself. It includes the faint interstellar material beyond that bubble, pressing gently at the edge. We live inside layers. The room around you, the atmosphere around Earth, the magnetic field around the planet, the solar system around the sun, the heliosphere around the planets. The local interstellar cloud around the heliosphere, the local bubble around the nearby clouds, the Milky Way around all of it. Each layer is real, and each one has its own scale, its own behaviour, and its own quiet influence. The local interstellar cloud also reminds us that the galaxy is not perfectly uniform. If the sun had been moving through a much denser interstellar cloud, the heliosphere might be compressed. More cosmic rays might reach the inner solar system. The night sky would still look familiar to our eyes, but the space environment around the planets could be different. If the surrounding medium were thinner, the heliosphere might expand farther. Over the long history of Earth, the solar system has likely passed through different interstellar environments as it orbited the galaxy. Some researchers study whether these passages could have influenced the amount of cosmic radiation reaching Earth, or left traces in isotopes found in ocean crusts, lunar samples, or Antarctic snow. These are subtle questions, and they are not simple. The Earth has many protective systems of its own, including its atmosphere and magnetic field, but the larger setting still matters. Our planet is not sealed away from the galaxy. It is protected, yes, but not completely separated. For tonight, though, we do not need to rush into all those effects. We can begin with the image of motion. You, perhaps lying still, listening quietly, are part of a moving system. The bed may feel still, The floor may feel firm, the walls may not seem to be going anywhere, but Earth is turning beneath you. The sun is carrying its planets through the galaxy. The heliosphere is meeting the interstellar medium. The local interstellar cloud is sliding past the edge of our solar bubble in a movement too large and too slow for daily life to notice. You're not still, and you have never been still. Stillness for us is local. It is a feeling our bodies make when the scale is small enough. On the scale of the galaxy, everything is travelling. There is comfort in that, I think. Not a dramatic comfort, not the kind that asks anything from you, but a simple one. We're moving through the galaxy without having to steer. The sun has been doing this work for billions of years, carrying its small family of worlds through changing regions of interstellar space. Earth has crossed seasons, ages, ice, warmth, extinctions, recoveries, and all the restless business of life, while the solar system continued its quiet galactic path. Tonight, the same motion continues. The planets keep their orbits, the solar wind keeps flowing outward, the interstellar atoms keep arriving from beyond the heliopause. The boundary keeps shifting, breathing with the sun's activity, responding to the faint pressure outside. So as we begin, let the idea settle gently. The solar system is moving through a thin interstellar cloud right now. Not storm, not a wall, not a glowing tunnel. A warm, sparse, magnetized flow of material in the local Milky Way. It surrounds the outer environment of the sun and helps shape the boundary between our star's influence and the wider galaxy. It is too faint to see, too thin to feel, and too large to cross in a human lifetime in any ordinary sense. But it is there. It is part of the answer to where we are. And once we know that, the next question becomes even more interesting. If the solar system is moving through the local interstellar cloud, then how fast are we moving? In what direction? What carries the sun around the galaxy, and why does our ordinary idea of sitting still become so beautifully misleading once we widen the view just a little more? The first thing to understand is that stillness is mostly a local feeling. Your chair may be still compared with the floor. The floor may be still compared with the walls. The walls may be still compared with the street outside, assuming you do not live somewhere with unusually ambitious architecture. But the moment we widen the view, that comfortable sense of rest begins to loosen. Earth is spinning. Earth is orbiting the sun. The sun is travelling through the Milky Way. The Milky Way itself is moving through the local group of galaxies. And you, without needing to pack a bag or remember where you put your boarding pass, are being carried along with all of it. This is not just a poetic way of saying that life is busy. It is a physical fact. Right now, while you listen, Earth is rotating toward the east. At the equator, that spin carries the surface around at roughly 1,670 kilometers per hour. If you're farther from the equator, your speed from Earth's rotation is lower, because you're travelling around a smaller circle each day, but you're still turning with the planet. That rotation gives us sunrise and sunset, the apparent drift of stars across the sky, and the very ordinary feeling that a day has passed. The strange part is that we do not usually feel this motion. The ground does not rush under your feet. The air does not constantly roar past you, because the atmosphere is turning with Earth too. Everything nearby shares the same motion, so your body treats it as normal. It is a bit like sitting inside a smoothly moving train with the curtains closed. If the ride is gentle enough, your cup of tea does not know it is travelling. Earth is also moving around the sun at about 30 kilometers per second. That is more than 100,000 kilometers per hour, which sounds less like a peaceful bedtime fact and more like something that should require a helmet. Yet we feel none of it directly because Earth and everything on it are falling around the sun together. Orbiting is not the same as being dragged along a track. Earth is in a continuous free fall, always pulled inward by the sun's gravity, always moving sideways fast enough to keep missing it. This is one of those ideas that seems ridiculous until you sit with it for a moment. The reason our planet does not drop into the sun is not because gravity is weak. It is because Earth has sideways motion. It falls, but the sun's surface curves away beneath that fall. So the planet keeps going around and around, not like a ball tied to a string exactly, but like a world following the shape that gravity gives to space. That orbit is not a perfect circle. Earth follows a slightly stretched path called an ellipse, though it is close enough to circular that most drawings exaggerate the difference. Once each year, we complete a loop around the sun. We call that a year because it is convenient, and because humans have always enjoyed turning enormous cosmic motions into calendars with small boxes for dentist appointments. But the year is more than a schedule. It is one full lap of our planet around our star. Every birthday is not just another number. It is also proof that you have ridden Earth all the way around the sun again. You may not have moved from your neighbourhood. You may not even have left the sofa much on certain weekends, which is entirely understandable. But on the scale of the solar system, you have travelled hundreds of millions of kilometres. The moon is moving too, orbiting Earth once every month or so, tugging gently on the oceans and helping stabilise Earth's tilt. The other planets are each following their own paths around the sun. Mercury races close to the sun, completing a year in only 88 Earth days. Neptune moves so slowly around the outer dark that it takes about 165 Earth years to complete one orbit. Every object is in motion. Asteroids travel through the inner solar system. Comets fall inward from distant reservoirs. Dust grains spiral and drift. Even the sun itself wobbles slightly because the planets pull on it. Jupiter especially is massive enough to tug the sun around the shared centre of mass of the solar system. So even at home, before we ever think about interstellar clouds, our cosmic neighbourhood is not fixed. It is a moving system made of many moving parts. But now we widen the view again, because the sun is not sitting still either. The sun is one star among hundreds of billions in the Milky Way, and it orbits the centre of our galaxy. This galactic orbit is not like Earth's orbit around the sun in every detail. The Milky Way is not a single central object, with stars simply circling it like planets around a lamp. It is a vast rotating galaxy made of stars, gas, dust, dark matter, stellar remnants, magnetic fields, and all kinds of complicated structures that make galaxy dynamics a very good subject for anyone who likes both mathematics and mild headaches. Still, the basic picture is clear enough. The sun moves around the galactic centre, carried by the gravitational pull of all the mass inside and around the Milky Way. Our star's speed around the galaxy is enormous, roughly in the range of a few hundred kilometres per second. At that pace, the sun takes about 225 to 250 million years to complete one orbit around the Milky Way. This span is sometimes called a galactic year. It's a lovely phrase, though it does make ordinary years feel slightly underdressed. 1 galactic year ago, dinosaurs were still in Earth's future, depending on where you start counting, and the continents were arranged very differently. The Sun has completed only about 20 or so orbits of the galaxy since it formed about 4.6 billion years ago. In human terms, the Sun seems ancient beyond imagining. In galactic terms, it is not a child, but it has not exactly been around the block many times either. This galactic motion means that the solar system is always passing through a changing stellar neighbourhood. Nearby stars are not fixed in place like nails in a ceiling. They have their own motions. Some move with us in broadly similar directions, others drift away. Some pass relatively close over long stretches of time, then continue onward. The night sky looks stable to us because human lives are short compared with stellar motion. The constellations seem permanent, ancient, almost carved into the dark, but they are temporary patterns. Over tens of thousands and hundreds of thousands of years, the familiar shapes distort. Stars slide slowly across the sky. Orion will not always look like Orion is. The Big Dipper will not always hold its shape. The sky is not a painted dome, It is a moving crowd seen from inside the crowd. This is where the phrase, "the solar system is moving through space," can become slightly tricky, because space is not a stage with one absolute rest position. Motion always needs a comparison. You can be still relative to your bed and moving relative to Earth's axis. Earth can be moving relative to the Sun, and the Sun moving relative to nearby stars. Astronomers choose different reference frames depending on the question. If we want to describe Earth's orbit, we use the Sun as a reference. If we want to describe the Sun's motion in the galaxy, we use the Milky Way. If we want to describe the direction from which interstellar atoms enter the heliosphere, we use the local interstellar medium as the reference. The motion is real in each case, but the answer depends on what you are measuring against. For tonight's journey, the most important comparison is between the Sun and the material just outside the heliosphere. The Sun is not simply moving through empty darkness. It is moving through the local interstellar medium, the thin mixture of gas, dust, plasma, and magnetic fields between nearby stars. Within that local medium are warm cloudlets, faint flows of partly ionized gas. The local interstellar cloud is one of these structures, so when we say the solar system is moving through the local interstellar cloud, we mean that, relative to that surrounding material, the Sun has a motion. Interstellar gas appears to flow toward the heliosphere from a particular direction, not because the cloud is rushing at us like weather on Earth, but because the Sun and the cloud are moving relative to one another. This gives our solar system something like a forward direction through its surroundings. Not forward in the sense of a spaceship with a window at the front and a snack cart in the back, but forward in the sense that the heliosphere has an upstream side. The solar wind blows outward in all directions, but the interstellar medium presses and flows around the outside. The balance between those pressures helps shape the heliosphere. For a long time, many people imagined the heliosphere like a comet, with a rounded front and a long tail streaming behind the Sun as it moved through the galaxy. That picture was simple and useful. It may also be incomplete. Modern spacecraft measurements suggest the heliosphere may be more compact and more bubble-like than the old comet tail image, shaped strongly by magnetic fields and particle flows. Space has a habit of being less tidy than our first diagrams. The heliosphere itself is made by the Sun's solar wind. The Sun constantly releases charged particles, mostly protons and electrons, into space. These particles stream outward past the planets, carrying part of the Sun's magnetic field with them. Near Earth, this solar wind can disturb our magnetosphere and create auroras, those curtains of light that appear near the poles when charged particles and Earth's magnetic field perform their complicated dance. Farther out, the solar wind continues into the cold distances beyond Neptune. Eventually it slows, becomes turbulent, and meets the pressure of interstellar space. That region is not a wall, but a broad transition. The solar wind does not simply stop as if it has hit a pane of glass. It changes. It is compressed, heated, deflected, mixed, and shaped by the outside environment. This is one of the reasons our motion through the galaxy matters. If the Sun were moving through a denser region of interstellar gas, the heliosphere could shrink. If the surrounding medium were thinner, it could expand. If the magnetic field outside were arranged differently, the heliosphere's shape could change. The solar system's boundary is not a permanent fence. It is more like the surface of a bubble in a moving stream. It adjusts to conditions. It responds to the Sun's activity, which rises and falls over the solar cycle. It responds to the interstellar medium beyond it. And while the inner planets continue their familiar orbits, the outermost protective environment of the solar system is always negotiating with the galaxy. There is something quietly humbling about that. We often imagine the Sun as the centre of our system, which it is in the local gravitational sense. The planets orbit it. Its light warms Earth. Its gravity holds the family together. But the Sun is also just another star moving through a galactic neighbourhood it did not choose. It has surroundings. It has weather outside its own bubble. It has a direction of travel, neighbours that change, and a history written not just in its own light but in the space it crosses. We live by the sun, but the sun lives in the galaxy. The solar system's motion is not a straight line through the Milky Way. As the sun orbits the galactic centre, it also moves slightly up and down relative to the galaxy's main disk. The Milky Way's disk is broad and thin compared with its full halo, but it has thickness, and stars can oscillate through it over time. The sun's path is therefore not a perfect flat circle. It is more like a long, slow, gently wavering track through the galaxy. The word gently is doing a lot of work there, because the speeds are enormous and the timescales are huge, but from our perspective the motion is smooth. There is no galactic speed bump that rattles the crockery. The path unfolds over millions of years. As we move, our stellar surroundings change. Today, our nearest stellar neighbour is Proxima Centauri, part of the Alpha Centauri system, about 4.24 light-years away. But it has not always been the nearest, and it will not always be the nearest. Stars pass one another over deep time. Some come within a few light-years, some perhaps closer, though truly close passages are rare. These encounters can gently disturb the distant outer regions of the solar system, especially the Oort cloud, that vast hypothetical reservoir of icy bodies far beyond the planets. A passing star does not need to come anywhere near Earth to matter. At the far edges of the Sun's gravitational influence, even a distant stellar passage can nudge comets and alter their long orbits. The same is true of interstellar clouds. The Sun has probably passed through different regions of the interstellar medium during its lifetime. It may have moved through thinner cavities, warmer clouds, and perhaps denser regions. We should be careful here, because reconstructing the Sun's exact path through past interstellar environments is difficult. The galaxy is not a neatly archived travel diary, but the general idea is sound. The Sun's surroundings change over time. The Local Interstellar Cloud is not the whole story of the Sun's galactic journey. It is the current neighbourhood, or at least a major part of the current nearby environment, depending on how scientists define the mixed region around us. Before this, there were other conditions. After this, there will be others. The timescales involved are not human timescales. If the solar system is near the edge of the Local Interstellar Cloud, or in a transition zone between local clouds, it may take thousands of years or more to move clearly into a different surrounding flow. That is short compared with a galactic orbit, but long compared with human civilization. This is one of the reasons the topic feels so strange. We are crossing a boundary, or perhaps moving within a blended region of local clouds, but not in a way anyone can watch over a weekend. There is no visible line approaching us in the sky, no countdown, no special evening when the sun officially exits one cloud and enters another, while astronomers hand it a small commemorative certificate. The change is gradual, measured through particles, spectra, and models. Still, even gradual motion is motion. The solar system is not sitting in a cosmic waiting room. It is travelling through a medium that has structure. The local interstellar gas has a direction, a speed, a temperature, a density, and a magnetic field. Neutral atoms from interstellar space can drift into the heliosphere because they are not easily controlled by magnetic fields. Some of them travel inward and can be detected by spacecraft. Charged particles behave differently because magnetic fields steer them. Dust grains can also enter, though their paths depend on size, charge, and electromagnetic forces. In this way, the outside galaxy sends tiny messengers into our solar neighbourhood. We do not feel them, but instruments can count them. The discovery of this local motion required a different way of looking. You cannot simply stare at the night sky and see the solar system moving through the cloud. The cloud is too thin. The motion is too slow across human time. Instead, scientists use subtle evidence. They examine how starlight is absorbed by atoms between us and nearby stars. They measure the flow of neutral helium atoms entering the solar system. They use spacecraft to detect particles from the heliosphere's boundary. They compare the directions and speeds of local clouds. Piece by piece, they build a picture of the sun's surroundings. It is not as visually satisfying as a photograph of Saturn, perhaps, but in its own way, it is just as remarkable. We are mapping the invisible weather around our star. The idea that the solar system is moving can also make everyday life feel slightly more interesting. When you look at the sun, you're not looking at a fixed center in a fixed universe. You're looking at a star in flight. When you see the planets in the night sky, they are not beads on a static necklace. They are companions being carried along a galactic path, each orbiting the sun while the sun orbits the Milky Way. The whole system is like a small, orderly dance taking place on a much larger moving stage. Earth loops the sun while the sun sweeps through the galaxy. The moon circles Earth while Earth circles the sun. The result is not a simple line or circle, but a layered motion, a braided path through space. There are popular animations that show the planets trailing behind the sun like a spiral as it moves through the galaxy. They can be visually striking, but some of them are misleading if they imply the planets are being dragged behind the sun in a vortex. The planets orbit in a plane that is tilted relative to the sun's motion around the galaxy. Their paths through galactic space are indeed more complicated than flat circles, because the whole solar system is moving. But the planets are not helplessly streaming backward like leaves behind a car. They are gravitationally bound to the sun, orbiting it according to the familiar rules of celestial mechanics, while the entire system moves together. It is a subtle difference, but an important one. The solar system is not a whirlpool chasing the sun. It is a family travelling together. To picture it more accurately, imagine walking through a quiet room while holding a small lamp, and around that lamp are tiny moths moving in circles. From your own point of view, the moths circle the lamp. From the point of view of someone watching from across the room, the moths follow looping paths as you walk. Both views are valid. It depends on the frame of reference. The planets orbit the sun, and the whole system moves through the galaxy. The same motion can look simple or complex depending on where you pretend to stand. And here is the wonderful part. We never actually get to stand outside the whole thing. We observe from within. Every measurement we make is made by instruments carried along with Earth, which is carried along with the sun, which is carried along through the galaxy. Science is our way of correcting for that. We build reference frames, we compare motions, we send spacecraft outward. We read the fingerprints in starlight. We admit that our natural point of view is not the only one. This is one of the great quiet achievements of astronomy. From a moving planet around a moving star inside a moving galaxy, we have learned that we are moving. That realization does not make home less stable. It does not make your room less real, or the ground less trustworthy, or tonight less peaceful. It simply places our stillness inside a larger motion. You can rest while Earth turns. You can sleep while the solar system crosses interstellar gas. You can feel calm while the sun carries everything familiar through the Milky Way. Motion does not always mean disturbance. Sometimes motion is the condition that has always held us. We were born into it. Every creature that ever lived on Earth lived inside this travelling system. The first cells, the first forests, the dinosaurs, the first humans looking up at stars, all of them were passengers on a planet orbiting a moving sun. So when we ask what the solar system is moving through right now, we begin by understanding that it is moving at all, not metaphorically, not as an idea, physically, constantly, smoothly, through the local galaxy, through faint material between stars, through a neighbourhood shaped by ancient stellar explosions and threaded with magnetic fields. The sun is not alone in empty space. It is travelling within an environment, and that environment is the next thing we need to look at more closely. Once you let go of the idea that the solar system is sitting still, the next idea becomes easier to hold. The sun is not simply shining into an empty darkness. It is moving through a real environment, even if that environment is so thin and quiet that it feels almost like nothing at all. Around us, beyond the familiar planets, beyond Neptune, beyond the region where sunlight still has enough strength to warm a world in any meaningful way, the sun's influence meets material that belongs not to the sun, but to the space between stars. This is where the local interstellar cloud enters the story. It is not a cloud in the earthly sense. It is not a white mass drifting across a blue sky. It is not full of water droplets. It will not gather into rain, and it will not politely ruin your picnic. It is a faint mixture of gas, dust, charged particles, and magnetic fields, spread so widely that the word cloud almost feels too heavy for it. Still, cloud is the word we use, because astronomy often borrows familiar words and stretches them until they are just about able to cover something enormous and strange. A stellar nursery can be called a cloud. A cold, dark region full of molecular gas can be called a cloud. A faint, warm flow of interstellar atoms around the sun can also be called a cloud. The local interstellar cloud is one of these nearby pieces of the interstellar medium, the material that fills the space between stars in the Milky Way. It surrounds our current solar neighbourhood, or at least forms a major part of the surrounding material through which the heliosphere is moving. Sometimes it is called the local fluff, which is a wonderfully gentle name for something that is actually a serious scientific structure. It sounds like a blanket. It behaves more like a thin galactic weather pattern. If you imagine a fog, you will need to make that fog almost impossibly faint. An ordinary fog on Earth is dense enough to hide trees, soften headlights, and make the world feel as if someone has turned the contrast down. The local interstellar cloud does none of that. It is too thin to block our view of nearby stars. It is too sparse to make space look misty. If you were floating outside the solar system, protected somehow from all the many things a human body does not appreciate about space, you would not see yourself surrounded by pale vapour. The stars would still shine, the blackness would still look black, the cloud would be present, but not visible in the way our eyes expect clouds to be visible. It is something known through measurement, not scenery. The density is the key. On Earth, even the air in a quiet room is crowded with particles. Every breath contains enormous numbers of molecules. Even a laboratory vacuum can contain far more particles than the local interstellar cloud. In this interstellar cloud, there may be only a fraction of an atom in each cubic centimetre, depending on what type of particle we count and which part of the cloud we're describing. That is so empty by ordinary standards that our everyday language begins to fail. We call it gas, but it is not gas like the air around you. We call it a cloud, but it is not cloud like mist above a field. It is matter spread very thinly across distances measured in light years, and yet because those distances are so large, the cloud can still contain a great deal of material overall. This is one of the tricks space likes to play. Something can be almost empty, locally, and still important across enormous scales. A single cubic centimetre of the local interstellar cloud may contain very little, but the cloud itself stretches across a region so large that it becomes part of the sun's galactic environment. The heliosphere, the sun's protective bubble, does not care only about whether the surrounding material is thick by human standards. It responds to pressure, motion, magnetic fields, ionization, and the flow of particles. Even a very thin medium can shape a very large boundary, if the boundary is also spread across the outer solar system. Space is delicate, but it is not empty of influence. The main ingredients of the local interstellar cloud are hydrogen and helium. That makes sense because hydrogen and helium are the most common elements in the universe. Hydrogen is the simplest atom, just one proton with one electron if it is neutral. Helium is the second simplest, and both were made in huge amounts in the early universe. Heavier elements exist too, but in much smaller amounts. Some of them are in gas, some are locked into tiny dust grains. These dust grains are not like dust under a bed, though the name invites the comparison and also makes the galaxy sound as if it badly needs a vacuum cleaner. Interstellar dust grains are tiny pieces of solid material, often containing silicates, carbon compounds, metals and ices in colder places. They are the remnants and products of stars, stellar winds, ancient explosions, and the long chemistry of the galaxy. Some particles in the local interstellar cloud are neutral, meaning they carry no overall electric charge. Others are ionized, meaning atoms have lost electrons and become charged. This matters because neutral and charged particles behave differently. Neutral atoms can slip through magnetic fields more easily. Charged particles are guided, bent, trapped, or deflected by magnetic fields. Since the local interstellar cloud is partly ionized, it is not simply a loose collection of drifting atoms. It is also a plasma environment, at least in part tied to electromagnetic behavior, and once magnetism enters the story, the cloud becomes more than a passive fog. It becomes a structured physical environment with fields and flows that help determine how it meets the heliosphere. The word warm is often used to describe the local interstellar cloud, but this too needs a careful bedtime translation. Warm interstellar gas can have temperatures of several thousand degrees. That sounds alarming, as if the solar system is passing through an invisible oven. But temperature in such thin gas does not mean what it means in a kettle, a bath, or a summer pavement. Temperature is related to the average motion of particles. In the local interstellar cloud, the particles can be moving quickly, so the temperature is high. But there are so few particles that they do not carry much heat. If you could somehow be there and survive all the other problems, it would not feel like standing near a furnace. There are simply not enough atoms nearby to transfer heat to you in the usual way. It is a very hot gas in the mathematical sense, and a very poor blanket in the practical sense. This is a useful reminder that space is often surprising because our instincts were made for Earth. On Earth, thick air, liquid water, warm skin, cold wind, pressure, sound and weather train us to interpret the world. In interstellar space, those instincts have to be adjusted. A cloud can be invisible. A warm gas can fail to warm you. A vacuum can contain a magnetic field. A boundary can exist without a wall. The local interstellar cloud is real, but it does not behave like a cloud we could walk through on a hilltop. It is more like a faint current in the ocean of the galaxy, except even ocean is far too dense a comparison. Perhaps it is better to say that it is a region where the almost empty space between stars has a particular character. Astronomers learned about this character by studying light. When starlight travels from a nearby star to us, it passes through whatever material lies in between. Atoms in interstellar gas absorb specific wavelengths of light. Each kind of atom has its own pattern, a set of spectral fingerprints. If hydrogen, helium, calcium, sodium, magnesium, or other elements are present, they can leave marks in the light. These marks are narrow, precise, and meaningful. They can tell scientists what the gas is made of, how fast it is moving, and sometimes how warm or turbulent it is. In this way, astronomers can study material that is too faint to photograph directly. They do not see a glowing cloud around the sun. They see tiny changes in starlight and work backward to the invisible material responsible. This is a patient kind of science. It does not begin with a dramatic image. It begins with lines in a spectrum, with comparisons between stars in different directions, with questions about which absorption features belong to which cloud of gas. Nearby interstellar space is not a single smooth substance. It appears to contain multiple small warm cloudlets or flows, each with slightly different motion. The local interstellar cloud is one of them. Another nearby flow is often called the G cloud. There are others as well in the cluster of local interstellar clouds around the Sun. Their edges are not as clean as borders on a map. They may overlap, mix, or transition gradually. This is why scientists sometimes discuss whether the Sun is fully within the local interstellar cloud, near its edge, or close to a boundary with another local cloud. It is not because the whole idea is vague. It is because the real material is complicated. Think of driving through patches of very faint mist at night, except the car is the solar system. The mist is made of atoms spread across light years. The road is the Milky Way, and the headlights are a star that also creates a giant protective bubble. So perhaps not exactly like driving, but close enough for a tired brain. You may pass from one patch to another without any hard line. The density changes, the temperature changes, the motion of the gas changes. From inside the car, you may not notice the transition at all. Only careful instruments tell you that the surroundings have shifted. The sun's journey through local interstellar material is something like that, but much slower and much larger. The local interstellar cloud is also part of a larger setting called the local bubble. The local bubble is a vast, low-density cavity in the interstellar medium around the Sun, probably carved out by supernova explosions in the past. Imagine massive stars living fast, dying violently, and blowing hot gas outward into the surrounding galaxy. Over time, repeated explosions can clear out a region, heating and thinning the interstellar medium. Inside or along parts of this cavity are warmer, partly ionized clouds like the one around us. The Sun is not simply in the middle of ordinary galactic material. It is in a region shaped by the lives and deaths of stars that came before it. That means the space around us has history. The local interstellar cloud is not just a location. It is part of an old story of stellar explosions, expanding gas, cooling material, and galactic recycling. This is one of the quiet ways the universe connects things. A supernova may happen far away and long ago, but its effects can help shape the environment through which the Sun later moves. Stars die, and the interstellar medium changes. Gas is heated, pushed, compressed, ionized, and stirred. Dust grains are shattered or formed. Magnetic fields are bent and carried along. Later, a different star, our Sun, passes through the resulting region with planets in tow. We tend to think of the solar system as self-contained, because the planets orbit the Sun, and because our daily lives are so strongly tied to Earth. But the Sun's larger environment was prepared by the galaxy. The cloud outside our heliosphere is not random emptiness, it is material with a past. The local interstellar cloud may be thin, but it is not perfectly uniform. Studies of nearby interstellar absorption lines suggest that local warm clouds can vary in temperature, turbulence, and density over relatively small astronomical distances. Small, in this case, still means enormous compared with Earth. A variation over thousands of astronomical units is small by interstellar standards, but enormous by human ones. 1 astronomical unit is the average distance from Earth to the Sun. Thousands of them take us deep into the outer regions of the solar system, so when astronomers say the cloud has structure on small scales, they are speaking the language of stars, not street maps. Still, the point is important. The local interstellar cloud is not a perfectly smooth soup. It has texture. This texture matters because the heliosphere responds to the surrounding medium. If the density of neutral atoms changes, if the ionized fraction changes, if the magnetic field direction changes, then the outer boundary of the heliosphere can change too. The effects are not something you would notice while making breakfast. Your toast will not leap up and announce that the interstellar turbulence has shifted. But at the scale of the solar wind and cosmic rays, these changes matter. The heliosphere is a dynamic boundary. The local interstellar cloud is one of the external conditions that helps shape it. The cloud also sends some of its neutral atoms into the solar system. Neutral helium atoms from interstellar space can pass into the heliosphere and travel inward because they are not easily controlled by magnetic fields. Spacecraft such as IBEX have studied these incoming neutral atoms, using them as clues to the local interstellar flow. The direction and speed of these particles helps scientists understand how the Sun is moving relative to the surrounding gas. It is an elegant method. Instead of needing to visit every part of the cloud, we study the particles that arrive. It is like learning about a distant forest by examining leaves carried down a river, except the leaves are atoms, the river is the interstellar wind, and the forest is a nearly invisible cloud between stars. Astronomy does this kind of thing often. It turns messengers into maps. The phrase interstellar wind is sometimes used for this flow of neutral particles into the heliosphere. It does not mean wind you could feel on your face. There is no breeze in the human sense. But because the sun and the local gas are moving relative to each other, atoms enter from a preferred direction, giving the appearance of a wind. This interstellar wind has been measured and studied for decades. It tells us that the solar system has an upstream side facing into the flow and a downstream side trailing away from it. Again, not like a boat crashing through water, but like a bubble moving through an extremely thin medium. The comparison is imperfect, but it gives the mind something to hold. It is tempting to ask whether this cloud is dangerous. The short answer is no, not in any immediate dramatic way. The local interstellar cloud is not dense enough to flood the inner solar system with gas. It is not about to smother the sun or dim the daylight. It is not some cosmic fog bank that will roll past Earth and turn noon into twilight. The heliosphere, Earth's magnetosphere, and Earth's atmosphere all help separate daily life from the raw conditions of space. The cloud's importance is subtler. It shapes the outer environment of the solar system. It affects the interaction between solar wind and interstellar material. Over long timescales and under different interstellar conditions, the surrounding medium could influence how many galactic cosmic rays reach the inner solar system. But the local interstellar cloud, as we know it now, is part of the ordinary current setting of our solar neighbourhood. That ordinary setting is still extraordinary when we slow down enough to notice it. Every second, the solar system is moving through this faint material. The planets continue their orbits inside the heliosphere, while the outer bubble of the sun presses against and interacts with the local cloud. Atoms from outside drift in. Solar particles stream out. Magnetic fields meet and shape the boundary. The whole arrangement is quiet, invisible, and ongoing. It is not a single event. It is a condition of being here. There is also a philosophical softness in this. We are used to asking where Earth is. The answer might be a street, a country, a planet, the third orbit from the sun. But there is a larger address too. Earth is inside the solar system. The solar system is inside the heliosphere. The heliosphere is moving through the local interstellar cloud, within the larger local bubble, inside the Milky Way. Each address is true at a different scale. None cancels the others. You're in your room, and you're in a galaxy. You're under a ceiling, and you're inside a moving solar bubble surrounded by faint interstellar gas. It is quite a lot for a person who may only have been trying to relax before sleep. The local interstellar cloud helps us understand that space is not divided into simple categories of here and there. There is no sudden jump from solar system to galaxy, no clean doorway where familiar space ends and interstellar space begins. Instead, there are layers of influence. Near Earth, the planet's atmosphere dominates. Farther out, Earth's magnetic field shapes charged particles. Beyond that, the sun's solar wind fills the heliosphere. Beyond the heliopause, the interstellar medium takes over. But even across those boundaries, particles and fields interact. Neutral atoms cross inward. Cosmic rays enter. Solar activity affects the shape of the outer bubble. The galaxy presses gently on the sun's domain. Boundaries exist, but they are living boundaries, not walls. This matters because it changes the meaning of the edge of the solar system. If we define the solar system by planetary orbits, Neptune is near the outer known planet region. If we include the Kuiper belt, we go farther. If we include the heliosphere, we go farther still, to the region where the solar wind yields to interstellar space. If we include the Oort cloud, the sun's gravitational influence may extend vastly farther than the heliosphere. So when we talk about what the solar system is moving through, we have to be clear about which layer we mean. The planets are moving inside the sun's bubble. The bubble itself is moving through the local interstellar cloud. The distant Oort cloud, if we include it as part of the sun's gravitational family, may extend into interstellar space far beyond the heliosphere. Home has more than one edge, and this is where the local interstellar cloud becomes especially interesting. It is not just outside the solar system. It is touching the boundary of the sun's influence in a physical way. It is the nearby galactic medium that the heliosphere must push against. It is the material that helps define the shape and scale of our protective bubble. If the heliosphere is the sun's extended atmosphere, stretched into space by the solar wind, then the local interstellar cloud is part of the surrounding weather. Very thin weather, yes, weather that would be unimpressive to anyone expecting rain, but weather all the same because it has conditions, motion, pressure, and change. The cloud's faintness also explains why humans live for so long without knowing it was there. The sky did not announce it. The planets did not reveal it. Even telescopes at first were better at showing bright objects than subtle gases between nearby stars. Only when spectroscopy matured, and later when spacecraft began sampling particles from the edge of the heliosphere, did our local interstellar surroundings become clearer. This is a common pattern in science. The universe is not only made of things that are obvious. Some of the most important structures are quiet. They wait for the right instrument, the right question, the right patient comparison of tiny signals. In a way, the local interstellar cloud is a reminder that our senses are not the full measure of reality. You cannot see it. You cannot touch it. You cannot hear it. It does not appear as a glowing band in the sky, but it is there, and its presence can be inferred from atoms, spectra, and the shape of the heliosphere. The world beyond our senses is not less real because it is subtle. It simply asks for different tools. So tonight, as you rest on a planet that feels solid beneath you, the solar system is moving through this thin interstellar fog. The word fog is useful only if we keep it gentle and almost transparent in our minds. It is not a fog that blinds. It is not a fog that wets the ground. It is a fog made of rare particles, soft pressure, and magnetic structure. It is the faint surrounding matter of our local place in the Milky Way. It is a cloud so thin that earthly emptiness seems crowded by comparison, yet large enough and real enough to help shape the outer boundary of the sun's domain. To follow the solar wind outward, we have to begin with something so ordinary that it is easy to forget how powerful it is. The sun is not just a bright disk in the sky, not just the reason the day begins and plants know what to do. It is also a restless star constantly releasing material into space. Every second it sends out a stream of charged particles, mostly protons and electrons, moving away in all directions. This stream is called the solar wind, and although the name makes it sound like a breeze you might feel on your face during an evening walk, it is not air, and it is not gentle in the ordinary earthly sense. It is plasma, a thin flow of electrically charged particles carrying the sun's magnetic field outward through the solar system. Near Earth, we notice the solar wind mostly when it misbehaves. It can disturb Earth's magnetic field, stir up geomagnetic storms, affect satellites, and help create auroras near the poles. Those curtains of green, red, and violet light are one of the few ways our eyes can see the sun's invisible reach, touching our planet's upper atmosphere. But most of the time, the solar wind passes by without making itself dramatic. It flows past Earth, past Mars, past the asteroid belt, past Jupiter with its enormous magnetic kingdom, past Saturn and its rings, past Uranus and Neptune, and onward into the dark. It keeps going long after sunlight has become weak and cold. It keeps going beyond the familiar planets, into regions where the sun is no longer a warm disk in the sky, but still remains the source of a vast moving bubble. That bubble is the heliosphere. The word comes from helios, the sun, and sphere, though the real shape is not a perfect sphere because space almost never reads our simple vocabulary before arranging itself. The heliosphere is the region dominated by the solar wind and the sun's magnetic influence. It is the extended environment of our star, inflated outward by the particles the sun releases. If the sun were a candle, the heliosphere would not be the light but the moving warmth of its breath, except the candle is a nuclear furnace, the breath is plasma, and the room is the local galaxy. so perhaps the comparison needs a little supervision. Still, the idea is useful. The sun does not end at its visible surface. Its influence stretches far beyond the planets. This is the protective bubble we live inside. Protective does not mean sealed. It does not mean nothing dangerous gets through. Galactic cosmic rays, high-energy particles from outside the solar system still enter. Interstellar neutral atoms can drift inward. Dust grains can sometimes make their way through. The heliosphere is not a wall with a lock. It is not a shield in a science fiction sense, glowing blue around the planets, while someone on a bridge says, "shields at 40%. It is a physical region where the sun's outward wind pushes against the surrounding interstellar medium. That pushing matters. It helps deflect and slow some incoming charged particles from the galaxy, reducing the amount that reaches the inner solar system. Earth then has its own defences as well, especially its magnetic field and atmosphere. So we live inside a series of protections layered like quiet cosmic coats. Imagine standing on Earth and thinking upward. First, there is the atmosphere, thick enough to breathe near the ground and thin enough to fade gradually into space. Then there is Earth's magnetosphere, shaped by our planet's magnetic field and pressed on by the solar wind. Beyond that, the sun's domain fills the whole planetary system. The solar wind does not stop at Mars or Saturn or Neptune. It stretches into the deep outer dark, forming a bubble so large that even light takes many hours to cross the distance from the sun to its edge. The inner solar system where Earth lives is deep inside that bubble. We are nowhere near the boundary. We are tucked well within it, like someone sleeping in a house while weather moves across the fields outside. But every bubble has an outside. The heliosphere expands into the local interstellar medium, and eventually the outward pressure of the solar wind becomes too weak to keep flowing freely. The first major transition is called the termination shock. That name sounds severe, as if the solar system has reached the final page of a contract, but it simply describes the place where the solar wind slows down abruptly from supersonic speeds. Supersonic here means faster than the speed at which pressure waves can travel through that plasma. When the solar wind reaches this region, it is forced to slow, heat, and become more turbulent because it is beginning to feel the pressure of the interstellar material outside. Beyond the termination shock lies the heliosheath. This is a broad outer region where the solar wind has slowed and become disturbed. It is no longer racing outward in the same clean way it did near the planets. It is hotter, more compressed, more complicated. The heliosheath is like the thickened skin of the bubble, though again it is not solid. It is a region of interaction, where solar particles, interstellar atoms, magnetic fields, and energetic particles all become part of a very large and very subtle negotiation. If the inner heliosphere is the sun speaking clearly, the heliosheath is the sun's voice becoming muffled as it meets the noise of the galaxy. Farther out is the heliopause, the boundary where the solar wind's influence gives way to interstellar space. This is the edge that Voyager 1 crossed in 2012, and Voyager 2 crossed in 2018. It is not the edge of the solar system in every possible definition, because the sun's gravity may hold distant Oort cloud objects far beyond it. But it is the edge of the heliosphere, the edge of the sun's wind bubble. Cross the heliopause, and you enter a region where the surrounding interstellar medium dominates more than the solar wind. The sun is still there, its gravity still reaches. Its light still travels, but its wind has lost the argument. The fact that we have measured this boundary directly is quietly astonishing. Voyager 1 and Voyager 2 were launched in 1977, long before many of the devices in your room were even ideas. They were built to visit the outer planets, and they succeeded beyond anything reasonable. Then they kept going. Year after year, decade after decade, they moved outward until they reached a place no spacecraft had ever been before. Voyager 1 crossed the heliopause and entered interstellar space. Voyager 2 followed, taking a different path and carrying instruments that offered another precious set of measurements. These spacecraft did not see a glowing wall. They detected changes in particles, plasma waves, magnetic fields, and cosmic rays. The boundary announced itself not with a signpost, but with data. It is a lovely thing, really, that the edge of the sun's bubble was found by elderly machines whispering across billions of kilometers. There is something almost bedtime story gentle about it, if bedtime stories included radioactive power supplies, plasma instruments, and the deep patience of mission engineers. The Voyagers are moving through darkness, but they are not lost. They are still telling us about the region where our solar environment meets the galaxy. Their signals are weak by the time they reach Earth, but they carry news from a place that once existed only in theory and models. IBEX gives us another way to understand the heliosphere. Unlike Voyager, IBEX did not travel to the outer boundary. It studies the boundary from much closer to Earth by detecting energetic neutral atoms. These atoms are created when charged particles in the outer heliosphere exchange electrons with neutral atoms from interstellar space. Once they become neutral, they can travel in straight paths, no longer strongly guided by magnetic fields. Some of them head inward and reach IBEX, carrying information from far away. It is an elegant trick. Instead of flying all the way to the boundary, IBEX catches messengers sent from it. One of IBEX's surprises was the discovery of a bright ribbon of energetic neutral atoms across the sky. Scientists did not expect it in that form, and it became a clue that the interstellar magnetic field outside the heliosphere has a major role in shaping the boundary. The heliosphere is not simply a balloon pushed evenly by gas. It is shaped by magnetic fields, particle pressures, solar activity, and the flow of local interstellar material. It is more complicated than a smooth shell. Depending on how scientists model it, it may look more like a rounded bubble, a croissant-like shape, or a structure with a tail and lobes influenced by magnetic forces. These descriptions may sound amusing, especially croissant-like, because it is difficult not to imagine the solar system wrapped in a pastry. But the point is serious. The heliosphere's shape is still an active scientific question, and new data can change the picture. For a long time, the heliosphere was often pictured like a comet, with a blunt nose facing into the interstellar flow and a long tail trailing behind. That image makes intuitive sense. If the sun is moving through interstellar material, perhaps its bubble should be swept backward, like a candle flame in a breeze. But measurements and models have shown that the real structure may not be so simple. The solar magnetic field, the interstellar magnetic field, energetic particles, and the solar cycle all complicate the shape. It may have a heliotail, but not necessarily the long simple tail once imagined. The universe often begins with a tidy diagram and then very politely refuses to remain tidy. The heliosphere also changes over time. The Sun has an activity cycle of roughly 11 years, during which its magnetic behavior, sunspots, solar storms, and solar wind conditions shift. When the Sun is more active, the solar wind can push differently. When it is quieter, the balance can change. These changes ripple outward, though slowly, because the solar wind takes time to travel to the distant boundary. The heliosphere is therefore not a frozen sculpture. It breathes with the Sun, expanding and contracting in subtle ways, adjusting to the changing pressure from inside and outside. Not like lungs exactly, but the comparison is tempting because it helps us understand that our solar bubble is alive with motion, not biologically alive, but dynamically active. The protective role of the heliosphere matters most when we think about cosmic rays. Galactic cosmic rays are high-energy particles, often protons or atomic nuclei, travelling through the galaxy at enormous speeds. Some come from supernova remnants or other energetic astrophysical sources. They can penetrate deep into the solar system, and when they strike Earth's atmosphere, they create showers of secondary particles. At ground level, Earth's atmosphere protects us from most direct effects, and our planet's magnetic field helps too. But the heliosphere reduces the incoming population before those particles even reach the inner solar system. It is not perfect protection. It is modulation, filtering, deflection, reduction. A cosmic umbrella with holes perhaps, but still better than standing bareheaded in a galactic particle drizzle. This is why the local interstellar cloud matters to the heliosphere. The outside medium helps determine how large and strong the bubble is. If the Sun were passing through a denser interstellar cloud, the heliosphere might be compressed closer to the Sun. A smaller heliosphere could allow more galactic cosmic rays into the inner solar system. If the surrounding material were thinner, the bubble might expand farther. The current local interstellar cloud is thin enough that the heliosphere remains large. But over millions of years, as the Sun moves through different regions of the galaxy, the external conditions can change. The protective bubble is not independent of where the Sun happens to be. There is no need to imagine this as an immediate danger. The local interstellar cloud is not pressing down on Earth. It is not changing the weather tomorrow. It is not the reason you slept badly last Tuesday, though it would be a rather grand excuse. The heliosphere's interaction with the cloud belongs to the scale of space physics and deep time, but it is still part of the real environment of our solar system. The cloud outside and the bubble inside form a boundary system, a meeting between the Sun and the galaxy. The heliosphere is also not symmetrical, because the Sun is moving relative to the local interstellar gas. There is an upstream direction where the solar system faces into the incoming flow of interstellar atoms, and a downstream direction where material is carried around and behind. But even this upstream-downstream picture is shaped by magnetic fields. Charged particles do not simply fly straight through space when magnetic fields are present. They spiral, drift, scatter, and interact. Neutral atoms, meanwhile, can move more freely until they are ionized or collide in ways that change their paths. So the outer heliosphere is a mixed region of different particle populations, each obeying rules that depend on charge, speed, energy, and field structure. It is an invisible machine with many moving parts. Because it is invisible, scientists often rely on indirect imaging. Energetic neutral atoms are one method. Plasma waves measured by Voyager are another. Cosmic ray changes can reveal transitions. Magnetic field measurements help show what region the spacecraft is in. No single instrument gives a perfect photograph. Instead, the heliosphere is understood through overlapping clues, like trying to understand the shape of a house by listening to rain on the roof, feeling drafts under the door, and catching letters that blow in from the garden. It is difficult, but not impossible, and each mission adds another piece. This makes the heliosphere feel less like a simple bubble and more like an active frontier. On one side is the Sun, sending out plasma and magnetic fields. On the other side is interstellar space, carrying neutral atoms, plasma, magnetic fields, and cosmic rays. Between them is not a wall, but a transition, thick and complex. The boundary is not only a place, it is a process. It is where solar material changes because of the galaxy, and galactic material changes because of the Sun. It is the conversation between our star and its surroundings. For Earth, deep inside the heliosphere, this conversation is usually quiet. Our daily life depends much more directly on sunlight, seasons, atmosphere, ocean, and weather. But the existence of the heliosphere is one reason our planetary environment is part of a larger shelter. It is not the only protection, and we should not overstate it. Earth's atmosphere and magnetic field are crucial, but the Sun's bubble adds a larger outer layer. The solar system is not exposed naked to interstellar space. It is wrapped in the extended influence of the star that formed it. There is something comforting in that, as long as we do not make it too neat. The heliosphere is protective, but not perfect. Vast, but not fixed. Real, but invisible. Shaped by the Sun, but also shaped by the local interstellar cloud around it. It is home, but home at a scale far beyond the planets. When we say we live in the solar system, we usually imagine orbits and worlds, but we also live inside a plasma bubble. We live inside a moving magnetic environment blown by the Sun into the surrounding galaxy. The planets are not just circling a star, they are travelling inside the star's extended atmosphere as it crosses interstellar space. If you could shrink the whole arrangement into something small enough to place on a table, you might see the sun at the centre releasing a constant flow. You would see planets embedded inside that flow. Farther out, you would see the wind slowing at the termination shock, thickening through the heliosheath, and finally meeting the interstellar medium at the heliopause. Outside, the local interstellar cloud would drift past, threaded by magnetic fields, sending neutral atoms inward and pressing gently on the bubble. But of course, we cannot place it on a table. The scale is too large. Even our fastest spacecraft take decades to reach the boundary. The heliosphere is not an object we can hold. It is a region we slowly learn to describe. The more we describe it, the more it changes the meaning of the sun. The sun is not only the bright centre of our days, it is also the maker of a boundary, the builder of a vast protective region around its planets. It shapes space far beyond the point where its warmth is obvious. Even in the cold outer dark, the sun is still active. Its wind still matters. Its magnetic field still travels outward. Its presence is felt at distances that make the inner planets seem close and cozy. And because the sun is moving, this bubble moves with it. The heliosphere is not left behind like smoke from a campfire. It is continuously created by the solar wind, continuously shaped by motion, continuously adjusted by the conditions outside. The solar system carries its bubble through the local interstellar medium. Or more accurately, the sun keeps inflating the bubble as it travels, and the galaxy keeps shaping the bubble from the outside. It is a balance, maintained moment by moment, across a region too vast for ordinary intuition. So when we imagine the local interstellar cloud, we should not picture Earth directly exposed to it. We should picture the cloud outside the heliosphere, meeting the outer reach of the solar wind. The cloud is the surrounding medium. The heliosphere is the sun's answer to it. Between them is the place where the solar system's private weather becomes galactic weather. That is the edge Voyager crossed. That is the boundary Ibex maps through atomic messengers. That is the frontier where our star stops being the dominant voice and the Milky Way begins to speak more clearly. The heliosphere is shaped by outside conditions, and those conditions come from the local interstellar cloud's mixture of atoms, ions, dust, and magnetic fields. But what are we really moving through? If this isn't just an invisible fog, but a structured physical substance with ingredients, temperature, electric charge, motion, and traces of ancient events in the galaxy. The word ingredients makes this sound almost too simple, as if the local interstellar cloud were a recipe. Add hydrogen, stir in helium, sprinkle with dust, fold in a magnetic field, leave to drift for a few million years, and serve cold between the stars. The real cloud is not that tidy, of course. Nothing in the interstellar medium arrives with measuring spoons, but thinking about what it is made of helps turn it from a vague invisible fog into a real physical place, with material, motion, temperature, charge, and history. The cloud may be thin enough to seem like almost nothing, but it is not nothing. It is a mixture, and every part of that mixture tells us something about where the solar system is, what surrounds the heliosphere, and what kind of galactic neighbourhood the sun is moving through right now. Most of the local interstellar cloud is gas, and most of that gas is hydrogen and helium. This should not surprise us too much, because the universe has always had a strong preference for hydrogen and helium. They are the old, simple elements, made in huge quantities in the early universe, long before planets, rocks, oceans, or anyone worrying about where they left their glasses. Hydrogen is the simplest atom, just one proton and one electron when it is neutral. Helium has 2 protons and usually 2 neutrons in its nucleus, with 2 electrons when neutral. Together, these 2 elements make up most ordinary matter in the cosmos. So when we move into the space between stars, even here in our local cloud, we find the same basic cast of characters. But the gas in this cloud is not all in the same state. Some atoms are neutral, keeping their electrons. Others are ionized, meaning they have lost electrons and become charged particles. This partly ionized nature is one of the most important things about the local interstellar cloud. A neutral hydrogen atom can move through magnetic fields without being strongly controlled by them, because it has no net charge. A proton, on the other hand, is charged, and charged particles do not simply drift wherever they please. They respond to magnetic fields. They spiral around field lines, scatter, stream, and interact with plasma environments. Electrons do the same in their own lighter, quicker way. So the cloud is not just a thin gas sitting quietly outside the heliosphere. It is partly a plasma, and plasma brings electromagnetic behavior into the story. That makes the cloud more complicated than a simple fog. A fog on Earth is made of tiny water droplets suspended in air. It moves with wind, thickens, thins, hides trees, and makes distant lights look soft. The local interstellar cloud is made mostly of atoms and ions, with an incredibly low density. It does not hide the stars. It does not glow in a way our eyes can see. It does not make space cloudy in a visual sense. But because part of it is ionized, it is tied to magnetic fields and electric forces. Those forces matter at the boundary of the heliosphere. The solar wind is also plasma, and when one plasma environment meets another, the meeting can become very interesting. Though interesting here means complex particle physics, not someone spilling soup at a dinner table, which is a different branch of interesting. The temperature of the cloud is another detail that needs careful handling. Astronomers often describe the local interstellar cloud as warm. In this context, warm means several thousand degrees. That sounds like a contradiction. How can a cloud around us be thousands of degrees and not roast everything? The answer is density. Temperature tells us about the average motion of particles, not how much heat you would actually feel. In the local interstellar cloud, the particles are moving quickly enough that the temperature is high, but there are so few particles in any given volume that the total heat content is very low. If you somehow placed a thermometer there in the ordinary way, it would not behave like a thermometer in air. There is not enough material to transfer heat as our everyday senses expect. The cloud is warm in the language of particle motion, but extremely thin in the language of touch. This difference is one of the little traps the universe sets for human intuition. We evolved in thick air, with pressure, weather, oceans, fires, warm skin, cold mornings, and all the practical lessons of living on a planet. Space does not always honour those lessons. A hot sparse gas can feel like almost nothing. A cold dust grain can survive between stars. A magnetic field can shape particles across enormous regions while remaining invisible. A cloud can be real without being visible. So we have to let the words shift a little. Warm does not mean cozy. Cloud does not mean mist. Wind does not mean breeze. Dust does not mean the grey fluff behind the cupboard, though that kind may also have a mysterious origin story if you have not cleaned for a while. Interstellar dust is one of the most fascinating ingredients in the cloud, even though it makes up only a small fraction of the material. These dust grains are tiny solid particles, often smaller than smoke particles, made from heavier elements and compounds. They may contain silicates, carbon-rich material, metals, and other substances produced or processed by stars. Some dust grains form in the cool outer atmospheres of aging stars, where material can condense before being blown into space. Others are shaped by supernova explosions, shocks, radiation, and collisions in the interstellar medium. They are small, but they carry history. A single grain of interstellar dust may contain atoms that were once inside a star, atoms forged in nuclear reactions or released during violent stellar death. That is why ancient starlight belongs in this story, even if the cloud itself is not shining brightly. The material in the local interstellar cloud has been exposed to starlight for a very long time. Nearby hot stars past supernovae, ultraviolet radiation, and the general glow of the galaxy have all helped shape its state. Radiation can ionize atoms, knocking electrons away. It can heat gas, alter chemistry, and change the charge of dust grains. The cloud is not simply leftover material sitting untouched. It has been bathed, stirred, and altered by the light and energy of stars. Some of those stars may be long gone. Their light, winds, and explosions help prepare the local region the Sun now crosses. This is one of the quiet connections that makes astronomy feel both large and intimate. The atoms outside the heliosphere are not separate from the rest of cosmic history. They are part of the long recycling of matter through the Milky Way. Stars form from gas. Stars shine. Stars make heavier elements. Stars lose mass through winds or explode. Their material returns to interstellar space. Clouds form, disperse, heat, cool, and mix. New stars are born from material that has been through previous generations. The Sun itself formed from a cloud enriched by older stars. Earth, your body, the calcium in bones, the iron in blood, the oxygen you breathe, all of these depend on that long recycling. The local interstellar cloud is not the source of all of that for us, but it belongs to the same galactic system of matter being reused, rearranged, and carried along. Dust grains in the local interstellar medium do not all behave the same way when they meet the heliosphere. Their paths depend on size, charge, speed, and how they interact with magnetic fields and solar radiation. Very small charged grains can be deflected more strongly. Larger grains may enter more easily. Some interstellar dust particles have been detected by spacecraft in the solar system, offering another way to study the material beyond the Sun's bubble. These grains are tiny messengers, not dramatic visitors. They do not arrive like comets lighting up the sky. They slip through space grain by grain, carrying physical clues about the environment outside. Gas atoms do something similar, especially neutral atoms. Neutral helium from interstellar space can pass into the heliosphere and travel inward toward the inner solar system. Because helium is neutral, it is less affected by magnetic fields than charged particles are. Spacecraft can detect this flow and use it to estimate the direction, speed, and temperature of the very local interstellar material. Hydrogen also enters, though it is more strongly affected by interactions at the boundary and by radiation from the Sun. These incoming atoms help scientists study the cloud from within the solar system. They are like faint visitors from beyond the edge, arriving quietly enough that only careful instruments notice them. Magnetism may be the least intuitive ingredient, because we tend to think of magnetic fields as things around magnets, wires, planets, or perhaps the small rectangle that keeps a fridge door shut with suspicious confidence. But magnetic fields thread interstellar space too. They are weak by everyday standards, but across huge distances they become important. The local interstellar cloud and the surrounding medium are threaded by the local interstellar magnetic field. This field influences charged particles and helps shape the outer heliosphere. It is one reason the heliosphere may not be a simple round bubble. The interstellar magnetic field presses, guides, and organizes the plasma environment beyond the heliopause. The solar wind carries the Sun's magnetic field outward. The interstellar medium carries its own magnetic field. At the boundary, these magnetic environments interact. This does not mean they snap together like toy magnets. Plasma physics is subtler than that. Charged particles move along and across field lines, waves travel through plasma, pressure balances shift, and the whole system becomes shaped by both motion and magnetism. Ibex's discovery of the energetic neutral atom ribbon gave scientists an important clue that the direction of the interstellar magnetic field was closely tied to what was happening at the heliosphere's edge. A ribbon across the sky may sound decorative, but in this case it was a sign that our local magnetic environment was leaving a pattern in the particles arriving from the boundary. The magnetic field also helps explain why the local interstellar cloud is not just a chemical mixture. It is a physical environment with structure, gas pressure, magnetic pressure, particle motion, ionization, dust, radiation, and turbulence all matter. The cloud may be thin, but it has properties. It has a flow direction relative to the sun. It has a temperature. It has a density. It has a fraction of atoms that are ionized. It has dust grains, magnetic field lines, and a larger galactic context. This is the difference between saying there is a cloud outside the heliosphere and saying there is a warm, partially ionized, magnetized interstellar flow around the sun's bubble. The second version is less cozy on a mug, perhaps, but it is closer to what the cloud really is. The gas is also not perfectly still. The local interstellar cloud has motion relative to the sun, which is why we speak of an interstellar wind flowing into the heliosphere. Again, wind here does not mean something that rustles leaves. It means a stream of particles entering from a preferred direction because of the relative motion between the sun and the local gas. This direction can be measured from incoming neutral atoms. The motion helps define the upstream side of the heliosphere, the side facing into the flow. It also contributes to the structure downstream, where the interaction continues in the opposite direction. The whole solar system is moving through this material, and the motion matters. The cloud's composition is not measured by scooping it into a jar. We do not have a bottle labelled Local Interstellar Cloud on a laboratory shelf, though if we did, it would look disappointingly empty. Instead, scientists use remote and indirect methods. They study absorption lines in the spectra of nearby stars. If starlight passes through gas between the star and Earth, atoms in that gas absorb specific wavelengths. Those wavelengths reveal which atoms are present. Shifts in the lines reveal motion. Widths and shapes can reveal temperature and turbulence. By looking in many directions, astronomers can piece together the structure of nearby interstellar clouds. It is slow detective work, but it is powerful. Spacecraft add another layer. IBEX measures incoming neutral atoms and energetic neutral atoms connected to the heliosphere boundary. Voyager measures conditions beyond the heliopause along its path. Other missions have measured dust, plasma, cosmic rays, and ultraviolet backgrounds. None of these gives a complete picture alone. Together they build one. This is how the invisible becomes known. Not by one dramatic discovery, but by many careful measurements that slowly agree, disagree, improve, and refine the model. And science in this area is not a single flashlight switched on in a dark room. It is more like many small lamps being placed around a very large, almost empty hall. There is also the question of where the cloud begins and ends. If this were a cloud on Earth, we might point to its edge in the sky and say, there. But the local interstellar cloud does not have a sharp outline. It belongs to a cluster of nearby warm clouds or flows. The sun may be within the local interstellar cloud, near its edge, or close to a transition with neighbouring local material, depending on exactly how the local velocities and boundaries are interpreted. This does not make the cloud imaginary. It means that interstellar clouds are natural structures, not boxes. Their boundaries can be gradual. Their material can mix. Their names are human attempts to describe real but messy regions. The larger local bubble adds another layer of history. The Sun is located inside a broad, low-density cavity in the interstellar medium. This cavity was likely shaped by ancient supernova explosions and the winds of massive stars. Within this larger cavity are smaller warm cloudlets, including the local material around the Sun. So the local interstellar cloud is not floating in isolation. It is part of a bigger local environment carved, heated, and structured by earlier generations of stars. When we talk about gas, dust, magnetism, and ancient starlight, we're also talking about a neighbourhood shaped by death and renewal. Massive stars exploded, hot gas expanded, cavities formed, cloud survived or condensed along the way. The Sun, much later, moves through this complicated aftermath. The phrase ancient starlight can also be understood more literally. The atoms and dust in the Local Interstellar Cloud are exposed to radiation from nearby stars and the broader interstellar radiation field. Ultraviolet light can ionize atoms. Starlight can heat dust grains. Radiation pressure can affect small particles. Cosmic rays, though not starlight in the ordinary sense, also move through the region and contribute to ionization and energy balance. The cloud's condition is partly a result of the light and particles passing through it. Even in darkness, the space between stars is not truly untouched. It is continually influenced by radiation. This becomes important when we ask why the cloud is partly ionized. Some of the ionization likely comes from ultraviolet radiation and the past energetic history of the local region. Hot stars and past supernova-related processes can affect how many atoms lose electrons. The ionization fraction tells scientists something about the cloud's energy balance, its exposure, and its history. A fully neutral cold cloud would behave differently. A fully ionized hot plasma would behave differently. The Local Interstellar Cloud sits in a middle state, warm, sparse, partly neutral, partly ionized. This middle state is exactly what makes it interesting at the heliosphere, because neutral atoms can enter, while charged particles and magnetic fields shape the boundary. It helps to imagine the ingredients as different kinds of travellers. Neutral atoms are quiet travellers. They can cross magnetic fields without paying much attention, at least until they interact with sunlight, particles, or charge exchange processes. Ions are guided travellers. They respond to magnetic fields and become part of the plasma behaviour. Electrons are quick travellers, light and reactive. Dust grains are heavy little travellers by comparison, though still tiny, carrying solid material and responding depending on their size and charge. Photons, the particles of starlight, are messengers that can heat, ionize, and reveal the cloud. Magnetic fields are not travellers in the same way, but they are the invisible tracks and tensions that help organize the charged material. Put together, these ingredients make the local interstellar environment more like a weather system than an empty stage. Of course, this is very sparse weather. If you are imagining a storm, soften it down until it almost disappears, then soften it again. The cloud is not forceful in the way Earth weather is forceful. It does not push the planets around. Its gravity is negligible compared with the Sun's hold on the solar system. It does not blow dust across Mars or ruffle Saturn's rings. Its influence is mainly at the outer boundary, where the solar wind has thinned enough for outside pressure to matter. That is where these ingredients become important. The gas provides particles and pressure. The ionized component participates in plasma interactions. The magnetic field helps shape the heliosphere. Neutral atoms slip inward. Dust grains add small solid messengers. Radiation helps maintain the cloud's state. The cloud's thinness also means that the sun can move through it without obvious visible drama. We do not see a bright shock wave ahead of the solar system. Earlier ideas sometimes included a possible bow shock, like the shock wave ahead of a supersonic object. But later measurements suggested the sun's motion through the local interstellar medium may not create a strong bow shock in the way once pictured. Instead, the interaction may form more of a bow wave or a gentler disturbance, depending on the magnetic field and local conditions. This is another example of the universe asking us to trade simple images for better ones. The solar system is moving through material, yes, but the exact interaction depends on speed, sound speed, magnetic properties, and particle pressures. It is not just a boat through water. When we say the cloud contains ancient starlight, then we're also saying that it contains memory. Not memory like a mind, but physical memory. The amount of ionization remembers past radiation. The dust remembers stellar formation and destruction. The gas composition remembers cosmic abundance and chemical enrichment. The magnetic field remembers the larger motions of plasma in the galaxy. The cloud's place inside the local bubble remembers ancient explosions. Every measurement is a clue to something that happened before humans, before mammals, before Earth, and in some cases before the sun itself. That is a lot for a cloud that we cannot even see. And yet this invisible cloud is part of our address. It is the material outside the heliosphere now. It is what the sun's bubble is moving through. It is the current local setting of our solar system in the Milky Way. The planets orbit inside the sun's protection, while this thin mixture surrounds the outer boundary. The gas and dust do not make our sky look different tonight. The magnetic field does not hum in our ears. The ancient starlight does not arrive labelled with its origin, but all of it helps define the environment just beyond the sun's reach. There is something grounding about knowing that even the space between stars has ingredients. It is easy to think of the darkness as a blank, but the blank is not blank. It contains hydrogen atoms moving through cold distances. It contains helium drifting inward from beyond the heliopause. It contains charged particles tied to magnetic fields. It contains grains of dust with atoms made in old stars. It contains radiation that has crossed long distances and altered what it touched. It contains the faint traces of earlier galactic events. The darkness is thin, but it is not empty. So the local interstellar cloud is made of gas, dust, magnetism, and the long influence of starlight, all spread across a volume so large that its faintness becomes meaningful. It is not dense enough to be seen as a fog, not warm enough in the practical sense to heat us, not solid enough to mark a border, and not dramatic enough to disturb daily life. But it is real enough to shape the heliosphere, real enough to send atoms into the solar system, real enough to be measured in starlight, and real enough to remind us that the sun is travelling through a living galactic environment. So how do we actually know any of this from inside the bubble, when Earth sits deep within the heliosphere, and most of the cloud lies beyond the region where the solar wind still dominates? Voyager 1 and Voyager 2 were launched in 1977, not to drift forever into the space between stars as their main public identity, but to visit the giant planets while the outer solar system was arranged in a rare and useful geometry. Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that a spacecraft could use one planet's gravity to help reach the next, like a very patient traveller catching connecting trains across a station so large that the platforms are hundreds of millions of kilometres apart. Voyager 1 visited Jupiter and Saturn. Voyager 2 visited Jupiter and Saturn too, then continued to Uranus and Neptune, giving humanity its only close looks at those two distant ice giants. These early missions already would have been enough to make the Voyagers legendary. They changed textbooks, filled image archives, and gave us storms, rings, moons, volcanoes, icy surfaces, blue planets, and a new sense of how alive the outer solar system could be. But after the planetary encounters, the spacecraft did not stop. There was no neat place to pull over. Space does not provide a little parking area beyond Neptune with a sign saying, "Thank you for visiting the planets." The Voyagers kept moving outward, away from the sun, each following its own path into the deep. Their cameras were eventually turned off because there were no more bright nearby worlds to photograph, and because power had to be conserved for instruments that could still study the environment around them. This feels almost strange when you think about it. The spacecraft that gave us some of the most famous images in space history continued their work by becoming less visual. They went from showing us planets to feeling the invisible structure of the solar system's edge. That word, feeling, is useful here, though we should use it carefully. Voyager did not feel the edge of the heliosphere the way your hand feels the edge of a table in the dark. There was no solid boundary, no thud, no sudden crossing from one room into another. The heliopause, the outer boundary of the heliosphere, is not a wall. It is a region where the solar wind's influence gives way to the interstellar medium. So Voyager had to identify the crossing through changes in particles, magnetic fields, plasma waves, and cosmic rays. It was a scientific threshold, not a doorway. Before reaching that threshold, each spacecraft travelled through the termination shock. This is the place where the solar wind, which had been racing outward from the Sun at supersonic speeds, slowed down sharply as it began to feel the pressure of the interstellar environment ahead. Then the spacecraft entered the heliosheath, the thick, turbulent outer region of the heliosphere. The solar wind there is slower, hotter, more disturbed, and less like the clean outward flow it was near the planets. In a familiar kind of map, we might draw this as a shell around the solar system, but even that is too tidy. The heliosheath is a changing, restless region of plasma, particles, magnetic fields, and interaction. It is not a smooth layer of wrapping paper around the Sun. It is more like the complicated place where the Sun's long breath becomes tangled with the surrounding galaxy. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed it in 2018. Those dates are easy to write down, but the achievement behind them is hard to hold. These spacecraft were launched when personal computers were young, when mobile phones were not part of ordinary life, when many of the people who now follow the mission had not yet been born. They crossed into interstellar space decades later, still powered by radioisotope generators, still sending signals back to Earth, still being listened to by human beings with antennas spread across our planet. A message from Voyager does not rush home like a text from a friend. It travels at the speed of light, but the spacecraft is so far away that even light takes many hours to reach us. When we receive a signal, we are hearing from the past, from a machine already farther along its path. What changed when Voyager 1 crossed the heliopause? One of the clearest signs was the change in particle environment. Inside the heliosphere, the spacecraft had been surrounded by particles associated with the Sun. As it moved beyond the heliopause, the number of solar particles dropped, and the number of galactic cosmic rays increased. That makes sense. The heliosphere helps shield the inner solar system from some incoming cosmic rays. Outside the bubble, Voyager was more exposed to the particle environment of interstellar space. The spacecraft had moved from inside the Sun's protective influence into the surrounding medium. It was still gravitationally bound to the Sun in a broad sense. It was still in the Sun's family if we define that family by gravity and origin, but it was no longer inside the solar wind bubble. This distinction matters because people often say Voyager left the solar system, and that can be both true and not quite true depending on what edge we mean. If the solar system means the region dominated by the solar wind, then Voyager crossed that boundary. If the solar system means the region where objects orbit the Sun, including the distant Oort cloud, then Voyager has a long way to go. The Oort cloud, if described as the distant reservoir of icy bodies loosely held by the Sun's gravity, may extend thousands or tens of thousands of astronomical units from the Sun. Voyager will not cross that whole gravitational frontier for a very long time, so it is more precise to say the Voyagers left the heliosphere and entered interstellar space. They crossed the edge of the Sun's wind, not the last possible reach of the Sun's gravity. Voyager 2 gave scientists a second crossing, and that was extremely valuable. One crossing is historic. 2 crossings begin to show that the boundary is not the same everywhere. Voyager 1 and Voyager 2 travelled in different directions and crossed the heliopause at different distances from the Sun. That helps scientists understand the shape of the heliosphere and how it changes. The heliosphere is not a perfect sphere. The interstellar medium presses on it from outside. The Sun's magnetic field and solar winds shape it from inside. The local interstellar magnetic field bends and organises the surrounding plasma. Solar activity rises and falls. All of this makes the boundary uneven and dynamic. The 2 Voyagers are like 2 small fingers touching different parts of an enormous invisible bubble and reporting back, "It feels different here." There is something wonderfully human about that. We could not see the whole boundary, so we sent instruments outward. Then, because the boundary was too large for 2 paths to describe fully, We built other ways to sense it from closer to home. That is where IBEX enters the story. The interstellar boundary explorer did not travel to the heliopause like Voyager. It stayed much nearer Earth in a high orbit and studied the heliosphere's edge from a distance. At first, that sounds almost impossible. How do you study a boundary billions of kilometers away without going there? The answer is that the boundary sends messengers inward, not on purpose, of course, because atoms are not known for their correspondence skills, but through physical processes that can be measured. IBEX detects energetic neutral atoms, often shortened to ENAs. These particles are created when charged particles in the outer heliosphere interact with neutral atoms from interstellar space. A charged particle can capture an electron from a neutral atom, becoming neutral itself. Once it becomes neutral, it is no longer strongly guided by magnetic fields. It can travel in a relatively straight line. Some of these energetic neutral atoms travel inward toward the inner solar system, where IBEX can detect them. By measuring where they come from and how energetic they are, IBEX can build a kind of map of what is happening far out near the boundary. This is a clever and gentle piece of cosmic detective work. It is a little like learning about waves beyond the horizon by catching sea spray that somehow flies straight to your window, although even that comparison is much too damp. IBEX catches particles, not photographs. Its maps are not images in the ordinary sense, like a picture of Saturn's rings. They are maps of particle counts and energies across the sky. They show where energetic neutral atoms are arriving from in greater or smaller numbers. From that, scientists infer the structure and behaviour of the outer heliosphere. And IBEX found something unexpected. It discovered a ribbon, a broad, bright arc of energetic neutral atoms across the sky. Before IBEX, scientists had models of what the heliosphere might look like in ENA emissions, but the ribbon was a surprise. It was not supposed to stand out in quite that way. It looked like a long strip of enhanced particle emission, almost circling the sky. For scientists, this was not just a pretty pattern. It was a clue that something about the interaction between the heliosphere and the local interstellar magnetic field was more important than expected. The ribbon seems to be connected to the direction of the interstellar magnetic field draping around the heliosphere. In other words, the galaxy outside our bubble was leaving a visible particle signature in the data. This ribbon changed the way researchers thought about the heliosphere. It suggested that the outside magnetic field was not just a background detail, but a major part of the boundary structure. The heliosphere is shaped not only by the solar wind pushing outward, but by the magnetic environment into which it pushes. The sun creates the bubble, but the local interstellar medium sculpts it. That means IBEX was not only feeling the edge of our solar home, it was also feeling the pressure, direction, and magnetic character of the neighbourhood beyond it. Voyager and IBEX work beautifully together because they sense the boundary in different ways. Voyager gives direct measurements along narrow paths. It is like sending a probe to touch the shoreline at two places. IBEX gives global maps from a distance, like looking at patterns in waves, foam, and currents to understand the whole coast. Neither method alone is complete. Voyager cannot be everywhere. IBEX does not physically cross the boundary. But together they let scientists compare the local with the global, the direct with the remote, the tiny path with the whole sky. There is another reason this matters. The heliosphere is not static. It changes as the sun changes. The sun has an activity cycle of roughly 11 years, with sunspots, magnetic activity, solar storms, and solar wind conditions rising and falling. Changes in the solar wind travel outward, eventually reaching the distant boundary. IBEX has watched the heliosphere over years, tracking how ENA emissions shift with time. This allows scientists to see the outer boundary not as a fixed shell, but as a responsive system. The sun's moods, if we may call them that gently, ripple outward through the heliosphere and alter the signals that return. The Voyagers also continue to measure interstellar conditions, though their power is slowly declining. Instruments have been turned off over time to conserve energy. The mission team has had to make careful choices, preserving the most valuable measurements as long as possible. This adds a bittersweet feeling to the story. The Voyagers are still out there, but they are aging. They are not immortal. Their voices will eventually fade. At some point they will stop sending data, and they will continue silently through the galaxy, carrying their golden records and their history with them. Long after communication ends, there will still be objects made on Earth travelling between stars, quiet, dark, and patient. For now, their measurements remain precious. Voyager 1 and Voyager 2 have helped reveal the plasma density beyond the heliopause, the behaviour of cosmic rays, the structure of magnetic fields, and the transition from solar to interstellar dominance. They showed that the heliopause is a real boundary in the particle environment. They confirmed that the sun's bubble has an edge that a spacecraft can cross. That is a remarkable thing. For thousands of years, humans looked at the night sky and wondered what lay between stars. Now, two machines have entered that between. IBEX, meanwhile, has made the invisible boundary more map-like. It has shown that the heliosphere's interaction with the interstellar medium is not bland or uniform. It has structure. It has a ribbon. It changes over time. It is shaped by magnetism in ways that were not fully expected. The mission gave us a way to image the edge of the solar system without light, using neutral atoms as messengers. That is a difficult idea, but a beautiful one. We are used to seeing by photons, by light bouncing off things or being emitted by them. IBEX lets us see in a different scientific sense by counting particles that have travelled inward from the outskirts of the sun's bubble. The edge itself is not a place where the sun vanishes. Even beyond the heliopause, the sun is still the brightest star from the perspective of Voyager. Its gravity still matters, its light still travels, but the plasma environment has changed. Inside the heliosphere, the solar wind is the main actor. Outside, the very local interstellar medium takes over. This is why the boundary is so meaningful. It marks a change in environmental control. On one side, the sun's wind dominates. On the other, the galaxy's surrounding material dominates. Voyager crossed from one regime into another. To make the scale feel a little more human, imagine the planets as being gathered close to a campfire. Mercury, Venus, Earth, and Mars are near the bright centre. Jupiter and Saturn are farther out, still clearly within the camp's warmth. Uranus and Neptune are near the cold outskirts, where the fire is small in the sky, but still the central light. Beyond them are icy bodies, dwarf planets, comets, and darkness. Yet the campfire's smoke, if we can call the solar wind smoke for a moment, keeps spreading outward far beyond the visible group. Eventually that smoke meets the surrounding night air. The heliopause is not the edge of the firelight, and it is not the last ember. It is where the outward flow from the fire loses its dominance to the air beyond. Voyager reached that place. IBEX studied it from afar by catching traces of the meeting. The edge of our solar home is also important because it helps define the environment that protects the planets. Without the heliosphere, the inner solar system would be more exposed to galactic cosmic rays. The sun's bubble does not remove that radiation completely, but it reduces and modulates it. Earth's atmosphere and magnetic field provide stronger local protection for life on the surface, but the heliosphere is the large outer layer, the first broad response of our star to the galaxy. Voyager and IBEX help us understand how that layer works. They help us understand how the sun shields its planets, how the shield changes, and how the surrounding interstellar cloud presses against it. This matters for more than our own solar system. Other stars have stellar winds too. Other stars move through interstellar material. Around them may be astrospheres, bubbles like the heliosphere, shaped by their winds and their local environments. If planets orbit within those bubbles, their radiation environments may depend partly on the strength of their star's wind and the density of surrounding interstellar space. By studying our heliosphere close up, we learn something about how stars and interstellar clouds interact elsewhere in the galaxy. The sun becomes our nearest laboratory for a process that may be common around many stars. It is worth pausing on how indirect and patient this knowledge is. We do not have a camera outside the heliosphere looking back, giving us a neat portrait of the sun's bubble. We have spacecraft along two paths, particle maps from near Earth, models built from plasma physics, measurements of incoming atoms, and starlight absorption lines showing the character of the local cloud. We have clues. The heliosphere is understood through the agreement and tension between those clues. This is why its shape is still studied. Some models show a long tail, others suggest a more rounded or croissant-like structure with two lobes. Data keeps sharpening the picture, but the picture is not finished. The edge of our solar home is not simple, and that is part of what makes it worth studying. There's a kind of humility in that. We can send spacecraft beyond the heliopause and still not know the entire shape of the bubble. We can map energetic neutral atoms across the sky and still debate how exactly the ribbon forms. We can measure particles from the local interstellar medium and still ask where one nearby cloud ends and another begins. Science is not embarrassed by this. It is built for it. Uncertainty is not failure when it is honest and measured. It is the space where better questions grow. The emotional side of Voyager and Ibex is gentle but strong. Voyager gives the story distance and endurance. Ibex gives it vision without a camera. Together they make the edge of the solar system feel less like an abstract idea and more like a place we have begun to know. Not a place with rocks and cliffs, not a place where an astronaut could stand and look around, but a place defined by changing particles and fields, a place where the sun's influence thins, a place where the local interstellar cloud becomes the dominant environment, a place that marks the transition between our star's private weather and the wider weather of the Milky Way. And perhaps that is the most useful way to think about what these missions felt. Voyager felt the edge by crossing it. Ibex felt the edge by listening to particles that came from it. One travelled outward until the sun's wind no longer ruled. The other stayed close enough to Earth to keep watch and built maps from returning atomic messengers. Both turned the invisible into information. Both showed that the solar system has an outer boundary that is active, shaped, changing, and connected to the interstellar cloud around it. So when we say that the solar system is moving through the local interstellar cloud, we are not guessing from a comfortable chair and a starry sky. We have machines that have touched the transition. We have particles that have carried news inward. We have measurements showing where the sun's bubble meets the galaxy. The edge of our solar home is not imagined. It is out there, distant and shifting, a broad frontier of plasma and magnetism, where the solar wind slows, the interstellar medium presses in, and the faint cloud between the stars begins to take over. Beyond the local interstellar cloud, the view opens into a larger and older structure, one that makes our nearby region of the Milky Way feel less like a quiet patch of ordinary space, and more like the inside of a great hollow, carved by events that happened long before human beings were here to wonder about them. The local interstellar cloud is the thin material close around the heliosphere, the immediate surrounding flow that the sun's bubble is moving through now. But that cloud does not float alone in the galaxy. It is part of a wider neighbourhood called the local bubble, a vast low-density cavity in the interstellar medium around the sun. If the local interstellar cloud is like the faint mist just outside the sun's protective bubble, then the local bubble is the larger room in which that mist is drifting, though even the word room becomes a little shy when the walls are hundreds of light years away and made of gas and dust rather than plaster and wallpaper. The local bubble is not an empty sphere with smooth edges. It is not a soap bubble floating neatly in space with the sun placed kindly at its centre, as if the galaxy had taken special care to arrange a calm neighbourhood just for us. It is irregular, stretched, lumpy, open in some directions, bounded by denser material in others, and connected to the surrounding interstellar medium in ways that astronomers are still mapping. The name is useful, but it can make the structure sound simpler than it is. A bubble in a glass of water has a clear surface. The local bubble does not. Its edges are traced by dust, gas, young stars, molecular clouds, and the places where interstellar material has been compressed. Its shape depends on what kind of measurement you use. Like many things in astronomy, it becomes clearer when we stop demanding that it behave like a familiar object and let it be what it is, a large, messy cavity blown into the Milky Way's gas by powerful stellar events. The basic idea is this: the space around the Sun is unusually thin compared with many other regions of the galactic disk. There is interstellar gas here, yes, and the Local Interstellar Cloud itself is proof that the region is not perfectly empty. But the wider volume around us has less dense material than the average interstellar medium. This low-density cavity is filled, at least in part, with hot, sparse plasma. Around it, in many directions, lie denser shells or walls of cooler gas and dust. These surrounding regions are where many nearby star-forming clouds are found. In recent years, three-dimensional maps of dust have allowed astronomers to see this structure much more clearly. Instead of guessing from flat sky maps, they can reconstruct where dust sits in space around the Sun, and those maps show the local bubble as a real three-dimensional feature in our neighbourhood. How did such a cavity form? The leading answer is supernovae. Not one single explosion, most likely, but a series of them. Massive stars live fast compared with stars like the Sun. They burn through their nuclear fuel quickly, shine fiercely, lose material through powerful winds, and many end their lives in supernova explosions. A supernova can blast gas outward, heat the surrounding medium, and carve a cavity into interstellar material. If several supernovae occur in the same general region over millions of years, their expanding shockwaves can overlap and combine, creating a superbubble, a large hollow structure in the interstellar medium. The local bubble appears to be one of these structures, the result of multiple massive stars dying and stirring the surrounding galaxy. This is where the quietness of our current surroundings becomes almost startling. We are living inside the aftermath of ancient violence. The calm local cavity around the Sun was likely shaped by stellar explosions strong enough to clear and heat great volumes of interstellar gas. The stars responsible are gone. Their light faded long ago. Their shockwaves have expanded, slowed, merged, and left behind a changed environment. Now, much later, the Sun moves through the interior of that cavity, carrying Earth, oceans, weather, forests, cities, and sleeping listeners through a region prepared by dead stars. It is not the kind of fact one notices while taking out the rubbish, but it is there all the same. Our quiet neighbourhood has a dramatic past. The local bubble may be roughly 1,000 light-years across, depending on how one measures its full extent, though the distance to its dust-trace surface varies strongly by direction. That variation matters. The bubble is not centred like a neat classroom globe around the Sun. In some directions, denser material may be relatively close. In others, the cavity extends much farther. It appears to open outward above and below parts of the galactic plane, and newer work has described a chimney-like extension, as if the bubble has broken through and allowed material or energy to connect toward the lower density regions above the Milky Way's disk. This does not mean there is a literal chimney with smoke curling upward, charming as that would be. It means the cavity's structure may channel material or connect the local disk environment to the halo above, giving the bubble a more open and irregular form than a closed shell. The Milky Way's disk is full of gas and dust, but it is not uniform. It has clouds, cavities, shells, filaments, tunnels, and bubbles. Massive stars are especially good at rearranging their surroundings. Before they die, their strong radiation and stellar winds push on nearby gas. When they explode, they add another powerful shove. Over time, regions around groups of massive stars can become riddled with cavities. The local bubble is one such cavity, and it may connect with or neighbour other large structures, such as the Loop 1 superbubble, associated with the Scorpius-Centaurus region. The local interstellar environment is therefore not a single isolated hollow. It is part of a larger patchwork of bubbles and shells, a kind of galactic foam made by star formation and stellar death. This is a useful image, as long as we keep it loose. Imagine the interstellar medium not as a smooth fog filling the galaxy evenly, but as something more like bread dough full of bubbles, or foam with cavities of different sizes, though much thinner, hotter, and more magnetized than anything you would want near breakfast. Stars form in denser clouds. Massive stars blow holes in those clouds. Supernovae expand those holes. Shells of swept-up gas can become places where new stars form. The galaxy breathes in this way, not biologically but physically. Gas gathers. Stars ignite. Massive stars die. Cavities open. Shells compress. New clouds form. The local bubble is one breath in that enormous cycle. Recent mapping has made this cycle feel more immediate because many nearby star-forming regions appear to lie on or near the surface of the local bubble. This suggests that as the bubble expanded, it may have swept up gas into a shell dense enough to help form new stars. The idea is not that the bubble politely placed every nearby nursery exactly where it belongs, like someone arranging flowers in a vase. Star formation is complicated, and many factors matter. But the geometry is striking. The surface of the bubble is not just an edge. It may be a place where old explosions helped gather material into conditions where new stars could begin. In that sense, the local bubble is both a remnant and a maker, an imprint of stellar death and a possible contributor to stellar birth. There is a deep continuity in that. Supernovae are often introduced as endings, the final blasts of massive stars. But in the interstellar medium, endings are also rearrangements. The material pushed outward by explosions can compress neighbouring gas. The heavy elements released by dying stars enrich the galaxy. The shock waves can destroy some dust grains and help form or expose others. The same event can be destructive in one place and creative in another. The local bubble's shell, traced by dust and nearby star-forming clouds, is a reminder that the galaxy recycles not only matter but structure. A death can carve a hollow, and the hollow's edge can become a nursery. The Sun, however, was not born in the local bubble. The bubble is much younger than the Sun. Our star is about 4.6 billion years old, while the local bubble is thought to have formed over the past tens of millions of years. That means the Sun entered this kind of environment during its long orbit around the galaxy. It has been travelling through the Milky Way for billions of years, passing through different regions of interstellar space. At some point in the more recent galactic past, by astronomical standards, it came to be inside this low-density cavity. It is a little like moving into a neighbourhood long after the builders have left, except the builders were exploding stars and the neighbourhood is hundreds of light years wide. This also means the local bubble is temporary. Not temporary in the sense of being gone next week or even next civilization, but temporary in the long life of the galaxy. Interstellar cavities evolve. They expand, cool, merge, break open, refill, and are reshaped by later events. The bubble may still be expanding slowly, though it has lost much of its earlier force. Its walls and openings will change. The Sun will continue along its galactic orbit. Eventually, over long timescales, our solar system may leave the local bubble or move into a different local structure. The interstellar neighbourhood is not permanent. It only feels permanent because human lives are brief. Inside this wider bubble, the local interstellar cloud is one of the small warmer clouds or cloudlets near the Sun. This may sound contradictory. If the local bubble is a cavity, why is there a cloud inside it? But cavities are not always completely empty. They can contain wisps, cloudlets, flows, and leftover or intruding material. The local interstellar cloud is denser and cooler than the hot, sparse plasma that fills much of the bubble, though it is still incredibly thin by earthly standards. It may have formed or survived where larger bubble structures interact. perhaps connected with material between the local bubble and neighbouring superbubbles. The details are still studied, but the broad picture is that our immediate cloud is a small local feature inside a much larger carved-out region. This layered structure matters for the heliosphere. The Sun's protective bubble is shaped by the material immediately around it, especially the local interstellar cloud or very local interstellar medium. But that local material exists because of the larger environment of the local bubble. The density, temperature, ionization, dust content, and magnetic field of nearby gas are all part of a history written by the bubble's formation and evolution. If the Sun were outside the local bubble, embedded in a denser cold cloud, the heliosphere could be very different. It might be compressed. The flow of neutral atoms inward could change. The cosmic ray environment could shift. We do not need to turn that into alarm. It simply reminds us that the Sun's outer boundary depends on the galaxy around it. The local bubble also helps explain why our immediate neighbourhood is relatively transparent. Dust blocks and reddened starlight. In regions with more dust, distant stars become harder to see and their light shifts in colour. Because the local bubble is low in dust compared with denser regions, we have a clearer view through our nearby interstellar surroundings. This does not mean there is no dust. There is enough dust at the bubble's boundaries for astronomers to map it, and enough nearby material to leave spectral fingerprints. But compared with dense molecular clouds, the local cavity is open and thin. Our view of the galaxy begins inside a hollow. There is something almost cozy about that, although the word cozy is doing astronomy a favour. We live in a relatively cleared-out pocket of the Milky Way. Around us, at great distances, are the dusty walls and clouds of a larger shell. Within the pocket are smaller wisps of material, including the local interstellar cloud. Inside that cloud moves the heliosphere. Inside the heliosphere orbit the planets. Inside one of those planets is a world with air thick enough for weather, oceans deep enough for tides, and living things capable of asking what the solar system is moving through. The scale steps inward like a set of nested boxes, each one strange in a different way. The discovery and mapping of the local bubble required a different kind of vision from the vision used to admire planets. Astronomers built maps of dust by measuring how starlight is dimmed and reddened at known distances. With accurate stellar distances from missions like Gaia, it became possible to create more detailed three-dimensional maps of nearby dust. These maps reveal where the dusty walls and clouds are located, allowing scientists to trace the bubble's shape. This is not like taking a photograph from outside the Milky Way. We're inside the structure. Mapping it is more like trying to understand the shape of a cave while standing inside it, with many faint lamps placed at different known distances. Every star becomes a probe. Its light tells us something about how much dust lies between us and it. The local bubble is also studied through X-rays, ultraviolet observations, gas absorption lines, and models of supernova history. Hot plasma can emit soft X-rays, though interpreting that emission has been complicated by other sources, including charge exchange processes within the solar system. Nearby interstellar gas leaves absorption features in starlight. Young stars and moving stellar groups help reconstruct where massive stars may have been in the past. No single clue tells the whole story. The bubble is assembled from many lines of evidence, like a very large puzzle in which some pieces are transparent and others keep drifting away. One of the most interesting parts of the story is that the Sun is not at the exact centre of the local bubble. This should not be surprising, because there is no reason the galaxy would arrange a cavity around us for dramatic effect. Though humans do have a long tradition of quietly hoping the universe has better stage direction. The Sun is simply inside the cavity, moving through it. The walls are nearer in some directions and farther in others. The bubble's surface is irregular. Some nearby molecular clouds and star-forming regions sit along its shell. There may be openings, tunnels, or chimney-like extensions connecting to other low-density regions. Our position inside it is not special in a cosmic sense, but it is special to us because it is where our measurements begin. When we look outward from Earth, then we are looking through local layers created by different processes. First through our atmosphere, then through the solar system's own dust and plasma environment, then through the heliosphere, then through the local interstellar cloud, then through the wider local bubble and its walls, and eventually into the broader Milky Way. Each layer affects what we see and how we measure. Some absorb light, some scatter particles, some shape cosmic rays. Some are almost empty but still physically meaningful. The universe is not just objects separated by nothing. It is objects embedded in environments, and environments embedded in larger environments. The local bubble's origin in supernovae gives us another way to think about safety and danger. Supernovae are dangerous if they occur close enough, but their ancient remnants also help create the conditions of our current neighbourhood. The explosions that carved the local bubble happened long ago and far enough away not to erase Earth's biosphere. Their effects are now part of the background environment through which the Sun moves. Some studies of radioactive ion isotopes on Earth and the Moon suggest that nearby supernovae in the past few million years may have left traces in the solar system, though connecting every trace to every structure is difficult. Still, the general idea is clear. Earth has not lived in total isolation from stellar events. The galaxy has reached us, faintly, through particles, dust, radiation, and the shaping of the space around the Sun. This does not mean the local bubble is something to fear. It is not an approaching blast wave. It is not a hollow that will collapse onto us tomorrow. It is the broad current setting of our stellar neighbourhood. Its violence is mostly historical. Its present influence is subtle. It gives us a low-density surrounding region, a wider context for the local interstellar cloud, and a reminder that the Milky Way's gas is sculpted by massive stars. If anything, it makes our local environment feel more interesting, not more threatening. We are living in the quiet aftermath of a busy stellar past. The bubble's surface, with its dust and star-forming clouds, also changes the way we think about nearby constellations and dark regions of the sky. Some familiar star-forming regions, clouds, and associations are not randomly scattered around us. Their positions can be connected to the larger three-dimensional structure of the local interstellar medium. The night sky may look like a flat dome sprinkled with stars, but behind that appearance is depth and architecture. Dust clouds lie at different distances. Young stars trace recent formation. Old cavities show where gas has been cleared. The local bubble is part of that hidden architecture, invisible to the unaided eye but present in the arrangement of the nearby galaxy. If the heliosphere is our solar home's outer weather shield, the local bubble is the broader neighbourhood weather pattern shaped by old supernovae. The two scales meet through the local interstellar cloud. This is why the journey from the Sun's protective bubble to the local bubble is not a detour. It is a widening of context. The heliosphere tells us how the Sun pushes outward. The local interstellar cloud tells us what immediately presses back. The local bubble tells us why the local interstellar environment has the character it does. Each layer explains the next. There is a quiet irony here. Space is often described as empty, but to understand the emptiness around us, we need a history full of events. The local cavity is empty because something cleared it. The surrounding walls are denser because material was swept there. Nearby star formation may be connected to old expansion. The Sun's current interstellar surroundings are thin because the local medium has been reshaped. Emptiness in astronomy is rarely just absence. It is often the trace left by motion, pressure, heat, gravity, and time. As you listen, nothing about the local bubble announces itself. There is no sound from its walls, no glow across the ceiling, no little vibration in the floor as the solar system moves through its interior. The Earth continues spinning, the Moon continues circling, the Sun continues releasing its wind, the heliosphere continues pressing into the local interstellar cloud, and around all of that lies this larger cavity, the local bubble, like a faint galactic hollow, holding our nearby stars and clouds within its old, supernova-shaped form. It can be comforting to imagine the solar system inside this layered structure, not because the layers make us invincible, but because they make our place more understandable. We are not lost in a featureless dark. We are in a particular region with a particular history. The sun is moving through a local cloud inside a broad cavity. That cavity was carved by massive stars that lived and died before our present human story began. Its walls may have helped gather material where new stars formed. Its interior gives our solar neighbourhood its sparse character. Its shape is still being mapped, because even the space closest to us remains full of unanswered details. And those unanswered details lead naturally to the next question. If the local bubble is the wider hollow, and the local interstellar cloud is the immediate flow around us, where exactly are we within that cloud right now? Are we deep inside it, close to its edge, passing between nearby cloudlets, or approaching a slightly different interstellar environment? The answer is not as clean as a border on a map, because the material around the sun is thin, blended and moving. But the question matters because even small changes in the surrounding medium can reshape the outer boundary of the heliosphere. If the solar system were driving along a road, we might ask whether we had entered a town, were leaving it, or were passing through the outskirts. There would be signs, there would be streetlights, there might be a suspiciously enthusiastic roundabout, but the local interstellar cloud does not work that way. It has no road sign, no fence, no clear front door, and no moment where the sun crosses a painted line, and suddenly everyone in mission control stands up to applaud. Interstellar clouds are natural flows of gas and plasma, and their edges can be soft, irregular, overlapping, and difficult to define from the inside. So when we ask whether we are entering, leaving, or crossing the local interstellar cloud right now, the most honest answer is that we are moving through very local interstellar material, and the exact identity of that material is still studied. The sun is either inside the local interstellar cloud near its edge, or in a mixed transition region where material from the local interstellar cloud and nearby cloudlets, such as the G cloud, may be interacting. That may sound like a scientist trying to avoid a simple answer, but it is actually the simple answer that nature has given us. The local interstellar medium is not a set of boxes. It is more like a set of faint currents in a very thin galactic sea. Where one current ends and another begins can depend on velocity, temperature, composition, and the direction you look. For a long time, the common picture was that the sun is travelling inside the local interstellar cloud. A warm, partly ionized cloud of gas sometimes called the local fluff. This is still a useful description, and it's why the phrase appears so often in explanations of our local galactic environment. The local interstellar cloud is nearby. It surrounds much of the immediate region around the heliosphere in many models, and it fits many observations of local interstellar gas. But as measurements improved, the picture became more detailed. Nearby space appears to contain several small warm clouds or flows, each with its own motion. The local interstellar cloud is one of them. The G cloud is another. There are also other nearby components, sometimes called the blue cloud or the AQL cloud in scientific studies. These are not fluffy cartoon shapes drifting around the sun. They are names given to faint patterns in gas motion and absorption lines, traced through careful observations. The difficulty is that we are trying to map the local interstellar medium from inside the heliosphere, and the cloud itself is almost empty by ordinary standards. We cannot simply look out and see where the edge is. A cloud on Earth might show a visible boundary against blue sky. The local interstellar cloud is too thin for that. Its atoms reveal themselves through subtle clues. They absorb tiny portions of starlight. They send neutral atoms into the heliosphere. They influence the particles and magnetic fields at the outer boundary of the sun's bubble. From these clues, astronomers reconstruct the shapes and motions of nearby clouds. It is good science, but it is not the same as measuring the walls of a room with a tape measure. One major clue comes from the light of nearby stars. When starlight passes through interstellar gas, atoms in the gas absorb specific wavelengths. These absorption lines are like fingerprints. They tell scientists what kind of atoms are present, how fast the gas is moving toward or away from us, and sometimes how warm or turbulent it is. By looking at many nearby stars in different directions, astronomers can build a three-dimensional idea of local clouds. If one star shows absorption from a certain flow and another does not, that helps place the cloud along those lines of sight. If the absorption lines shift differently in different directions, that reveals motion. This is how an invisible cloud becomes a mapped structure. But the map is not simple. In some directions, the local interstellar cloud seems to be present. In others, different local cloud components appear. In some models, the LIC has an irregular shape and the Sun is close to a boundary. In others, the nearby gas is understood as a more continuous structure, not a set of separate little clouds. In still newer interpretations, the material immediately around the heliosphere may be a mixture, with properties that do not match the local interstellar cloud alone or the G cloud alone. This is not a failure of astronomy. It is what happens when nature gives us a region where gas flows are touching, mixing, slowing, and changing. Neutral helium gives another important clue. Helium atoms from interstellar space can enter the heliosphere because they are neutral, and therefore not strongly steered by magnetic fields. Spacecraft can detect this flow of interstellar helium. By measuring its direction, speed, and temperature, scientists can estimate the properties of the very local interstellar medium, the material just outside the heliosphere. If the helium flow matches the expected motion of the local interstellar cloud, that supports the idea that the Sun is inside the LIC. If it does not match cleanly, then something more complex may be happening. Recent work has suggested that the flow detected near the Sun may be more consistent, with a mixture of material from the local interstellar cloud and the neighbouring G cloud than with either cloud by itself. That is a very important point, because it changes the question from are we in the local interstellar cloud to what exactly is the local material touching the heliosphere made from. The name matters less than the physical conditions. The heliosphere responds to density, pressure, ionization, magnetic field, and relative motion. If the gas around us is a mixed region between clouds, then the boundary of the Sun's bubble is being shaped by that mixture. The cloud name helps astronomers organize the map, but the heliosphere feels the actual particles and fields. There is another gentle complication. These clouds are moving. The Sun is moving too. So even if we could define a perfect edge, it would not be fixed forever. The solar system is crossing the local interstellar medium as part of its larger motion around the Milky Way. Over thousands of years, the Sun changes its position relative to these cloudlets. Some estimates suggest the Sun may have entered the local interstellar cloud within the last several thousand years. Some models suggest it could leave the LIC or leave the current local cloud environment within the next few thousand years. But these numbers depend on how the cloud boundaries are defined and how the local flows are modelled. It is better to think of them as rough astronomical estimates, not calendar appointments. No one needs to mark a date for the Sun's cloud exit in a diary. There will be no morning when the weather forecast says mostly cloudy, with a chance of leaving the local fluff after lunch. The transition is slow. It happens over enormous distances and long times. If the Sun is approaching or passing through a boundary between local cloud materials, that boundary is likely diffuse. The heliosphere would adjust gradually as the surrounding density, magnetic field, and ionization conditions changed. The outer bubble might shrink or expand. The flow of neutral atoms entering the solar system might shift. Cosmic ray modulation might change subtly. But this is not like Earth crossing from one air mass into another and suddenly getting a storm. Interstellar changes are usually slow on human timescales. There are exceptions in the broad history of a star's journey, of course. If the Sun were to enter a much denser interstellar cloud, the heliosphere could be compressed more strongly. That would matter. But the current local environment is extremely thin. Whether we are inside the LIC in a boundary region or in a mixed LIC-G- cloud flow, we are not plunging into a dense nebula. We are moving through faint, warm, sparse material inside the larger local bubble. The difference is scientifically meaningful, but not a sudden threat to ordinary life on Earth. Your kettle is safe from the local interstellar cloud. Your socks, however, remain at risk from unknown household physics. It may help to picture the sun travelling through a patchy region of very faint mist, but with one important correction. The mist is so thin that a better word might be suggestion. There are slightly different flows, slightly different densities, and slightly different motions. The sun's heliosphere moves through them. At any moment, the material just beyond the heliopause has specific properties. Scientists want to know whether those properties belong mainly to the local interstellar cloud, to a neighbouring cloud, or to a mixture between them. The answer changes how we understand our current galactic address. From Earth, this can feel almost impossibly remote. We're used to borders that are visible or political or practical. A shoreline, a fence, a doorway, a national boundary on a map. But interstellar cloud boundaries are defined by physics. One region of gas may move at one velocity. Another may move slightly differently. One may have a different temperature or ionization level. They can overlap along a line of sight. They can be compressed, decelerated, or stirred by nearby hot gas and magnetic fields. The boundary is less like a wall and more like the place in a river where two currents meet and swirl together. You can point to the general region, but not always to one exact molecule, and say, "Here, this is the border." The local interstellar cloud and G-cloud are especially interesting because they are both very close in the local interstellar environment. The G-cloud is associated with the direction toward the galactic centre and nearby stars like Alpha Centauri in some maps. The local interstellar cloud has often been used to describe the immediate surrounding cloud of the Sun, but measured flows of interstellar helium suggest that what actually reaches the heliosphere may not line up perfectly with either cloud's expected motion. This has led to the idea of a mixed cloud medium around the heliosphere. If that is correct, then the Sun may be passing through a contact region where local cloud materials are interacting. This kind of interaction would not be surprising. The interstellar medium is full of motion. Clouds do not have to remain separate forever. They can meet, shear, compress, and exchange material. Their magnetic fields can affect how they interact. Their different velocities can create turbulence or mixing. A warm, partially ionized cloud is not a rigid object. It can be stretched and distorted. One study of the local cloud even described the surrounding cloud as behaving in a way somewhat like a squashed balloon, with gas being differentially slowed in one direction and expanding in others. That is not an image you need to take literally, but it gives a useful sense of how flexible and non-rigid these structures are. So, are we entering the cloud? In one sense, probably not newly entering the LIC right now, because the Sun has likely been in this kind of local interstellar material for thousands of years. Are we leaving it? Possibly. Depending on which model you trust and how you define the LIC's boundary, are we crossing it? Yes, in the broad sense that the Sun is always crossing through local interstellar material as it moves through the galaxy. We are not stationary inside a cloud. We are travelling through it, or through its edge, or through its mixed outskirts. The safest and most accurate bedtime answer is that the Sun is currently moving through a very local, low-density interstellar environment associated with the local interstellar cloud and nearby cloudlets, and it may be near a transition rather than deep inside a single clean cloud. This sounds less tidy than saying, "We're in the local interstellar cloud," but it is more interesting. It means our solar neighbourhood is not a static bubble sitting in a static fog. It is a meeting place. The solar wind pushes outward. The local interstellar medium presses inward. The Sun moves relative to nearby cloud flows. Neutral atoms arrive from outside. Magnetic fields shape the boundary. Dust grains slip through or are deflected. The whole system is dynamic. even though it changes slowly from our point of view. The heliosphere is the part of the story that would feel these changes first. If the surrounding interstellar density rose, the outside pressure on the heliosphere could increase. The heliopause could move inward. If the external pressure fell, the heliosphere could expand. If the interstellar magnetic field direction changed, the shape of the heliosphere could shift. If the neutral atom flow changed, ibex-like measurements would detect a different incoming pattern. These are the kinds of changes scientists watch for, model, and reconstruct. They are not visible in the night sky, but they are written in particles. The Voyagers help here too, though only along their paths. Voyager 1 and Voyager 2 crossed the heliopause in different directions, giving direct measurements of interstellar conditions outside the solar wind bubble. They do not tell us everything about the cloud, because two paths through an enormous boundary are still only two paths, but they show what the local interstellar medium is like just beyond the heliosphere in those directions. Combined with ibex, absorption lines, and neutral helium measurements, they help scientists understand whether the surrounding medium is uniform or varied. The answer, unsurprisingly, is varied. It is also possible that the Sun's local environment has changed significantly in the geologically recent past. Some radioactive isotopes found on Earth, the Moon, or in Antarctic snow have been linked by researchers to nearby supernova activity or interstellar dust carrying material through the solar system. These links are complex and should not be oversimplified, but they remind us that the solar system's environment is not closed. The galaxy can leave faint traces here. Dust can enter, cosmic rays can change, ancient stellar events can shape the local medium. When the Sun crosses different interstellar surroundings, Earth remains protected by many layers, but not completely isolated from the larger galaxy. That idea can feel both grand and strangely intimate. The solar system's motion through cloud material is not something we experience directly, yet it is part of the setting in which Earth exists. We often talk about Earth's environment as if it ends at the top of the atmosphere. For many practical purposes it does, but scientifically, the environment extends outward. Earth sits inside the solar wind sits inside the heliosphere sits inside the very local interstellar medium. The very local interstellar medium sits inside the local bubble. These are not just names, they are physical layers, each with its own behaviour. The question of entering or leaving a cloud is really a question about which layer surrounds our solar shield at this time in the Sun's journey. If humans could live long enough to watch the Sun pass from one local cloud into another, what would they see? Not much with the naked eye. The stars would not blink, the sky would not change colour, the planets would continue their orbits, but instruments would notice. The direction and temperature of incoming neutral atoms might shift. The heliosphere's boundary might move. Cosmic ray levels in the inner solar system might adjust over long periods. Dust flow could change. Space weather models would need to account for new outside conditions. It would be a transition measured in data, not drama. This is why the question is so well suited to quiet thinking. We are crossing something vast and real, but not in a way that demands panic or spectacle. It is more like realizing that a ship has been moving across a calm ocean all night while everyone aboard slept. The sea changed beneath it. The currents shifted. The wind altered slightly, but inside the cabin the lamp stayed steady. Earth is that cabin, in a sense, though much more complicated and with better gravity. We rest inside local stability while the larger environment changes over time. There is a useful humility in saying we do not know the boundary perfectly. The local interstellar cloud is nearby in astronomical terms, but it is still hard to map. The Sun's immediate surroundings are measured through tiny signals, and different models emphasize different evidence. Some portray the local cloud as one continuous structure around us. Others divide the region into several cloudlets. Recent work points to mixing near the heliosphere. The best answer is not a single dramatic label, but a careful description. The solar system is moving through sparse, warm interstellar material in the local cloud complex, and the Sun may be near or within a transition between named cloud flows. That careful answer does not make the story smaller. It makes it more real. Real space is messy. Real clouds have uncertain edges. Real measurements come with error bars. Real boundaries blur. The solar system is not travelling through a simple diagram. It is moving through a physical galaxy with overlapping flows, ancient supernova cavities, magnetic fields, and thin gas that can only be understood through patient evidence. This is exactly what makes the local interstellar medium so fascinating. It is not distant enough to be irrelevant, but not close enough to be obvious. It is the hidden neighbourhood just outside our solar door. For now, the Sun continues through this very faint region. Whether we call it the local interstellar cloud, the edge of it, or a mixed cloud flow, the practical image remains the same. Our star is wrapped in its heliosphere, and that heliosphere is moving through sparse interstellar material inside the larger local bubble. The outer boundary is being shaped by what it meets. The solar system is neither still nor isolated. It is part of a moving, changing, layered galaxy. And if the surrounding cloud material can change the size and shape of the heliosphere, then the next question becomes more personal. What could interstellar weather mean for the planets inside? Could a different cloud alter the radiation environment around Earth? Could the galaxy, in subtle ways and over long times, shape conditions for life without ever touching the ground directly? To answer that, we have to bring the story inward again, from cloud edges and heliopause crossings back toward planets, atmospheres, magnetic fields, and the delicate shelter that makes Earth feel so calmly separate from the deep space it is travelling through. Because the phrase interstellar weather sounds, at first, a little too dramatic. It makes you imagine a forecast delivered by a very tired astronomer, perhaps saying, "Tonight will be mostly hydrogen, with scattered helium, mild magnetic turbulence, and a small chance of cosmic rays before morning." It is a charming thought, but interstellar weather is not weather like rain, wind, snow, or a gloomy Tuesday sky. It is not something that rattles windows or changes what you wear outside. It is the slow changing condition of the space around a star, the density of the gas, the strength and direction of magnetic fields, the amount of ionization, the pressure from particles, the flow of dust, and the cosmic radiation that moves through the galaxy. For Earth, most of this feels very far away. You do not wake up and notice the heliosphere has shifted slightly. You do not step outside and feel the local interstellar cloud brushing against your face. The atmosphere, thankfully, is very good at being the atmosphere, which is one of its better habits. It gives us pressure, warmth, weather, and protection from much of the radiation that would otherwise make the surface of a planet a very unfriendly place. Earth also has a magnetic field, which forms a magnetosphere around the planet, helping deflect charged particles from the Sun and from space. And far beyond that, the heliosphere adds another broad protective layer around the planetary system. So life on Earth is not standing naked in the interstellar wind. It is deeply layered inside shields. Still, shields are not the same as isolation. Earth is protected, but not removed from the galaxy. The heliosphere does not block every cosmic ray. The magnetosphere does not prevent every energetic particle from reaching the atmosphere. The atmosphere does not erase every trace of space. Some high-energy particles from outside the solar system do reach Earth's upper atmosphere, where they collide with atoms and molecules and create cascades of secondary particles. These interactions can produce cosmogenic isotopes, such as carbon-14 and beryllium-10, which can be recorded in natural archives like tree rings, ice cores, and ocean sediments. In that sense, the galaxy does leave faint fingerprints on Earth. Not loud fingerprints, not the sort that kick open the door, but subtle traces written in atoms. The heliosphere helps regulate how many galactic cosmic rays enter the inner solar system. Cosmic rays are not rays in the everyday light beam sense. They are high-energy particles, often protons or atomic nuclei, travelling through space at tremendous speeds. Many are thought to be accelerated by powerful astrophysical events such as supernova remnants, though the full story of cosmic ray origins includes several sources and energies. When these particles enter the heliosphere, they do not simply glide straight to Earth without interruption. The solar wind, the Sun's magnetic field, turbulence, and the changing conditions of the heliosphere all affect their paths. During periods of stronger solar activity, the heliosphere can be more effective at reducing lower energy galactic cosmic rays reaching Earth. During quieter periods, more can enter. Even without changing interstellar clouds, the Sun itself already changes the radiation environment around the planets. Now add the surrounding interstellar medium to that picture. The size and shape of the heliosphere depend on the balance between the solar wind pushing outward and the external medium pressing inward. If the Sun moves through very thin material, the heliosphere can remain large. If the Sun moves into denser material, the outside pressure can become stronger and the heliosphere may shrink. If the interstellar magnetic field changes direction or strength, the shape of the heliosphere can change. If the ionization state of the surrounding gas changes, the flow of neutral atoms and charged particles at the boundary can change. This is what interstellar weather means for the solar system. It is not a storm in the sky. It is a change in the conditions outside the Sun's bubble that alters the bubble itself. The Local Interstellar Cloud, where the Sun is currently moving through very sparse warm material, is not dense enough to crush the heliosphere close to Earth. Our present interstellar weather is mild by the standards of the more extreme possibilities scientists model. The heliosphere remains vast, extending far beyond the planets. The Sun's solar wind still dominates the region around Earth. The Local Interstellar Cloud matters scientifically because it shapes the outer boundary, not because it is about to flood the inner solar system. This is a good place to breathe out a little. The cloud is real, but it's not a hidden doomsday fog. It is more like the surrounding climate of the Sun's outermost environment, extremely thin, slow changing, and important mainly when we think on enormous scales. Over the long history of the solar system, though, the Sun may have passed through different interstellar environments. Some regions of space are much denser than the Local Interstellar Cloud. Dense clouds, especially cold clouds, can contain far more material. If the Sun were to encounter one, the heliosphere could become much smaller. In some extreme models, a dense enough cloud could compress the heliosphere so far inward that Earth's orbit might spend time outside the Sun's usual protective bubble, or at least experience a very different particle environment. This is not the situation now. It is a possible kind of past or future galactic weather, the sort of thing researchers study to understand how a star's surroundings can change over millions of years. If such a compression happened, what would it mean for planets? The first effect would be on radiation exposure. A smaller heliosphere could allow more galactic cosmic rays into the inner solar system. Earth's magnetosphere and atmosphere would still matter greatly, but the radiation environment at the top of the atmosphere could change. More energetic particles interacting with the atmosphere could alter the production of certain isotopes. This is why scientists look at cosmogenic records when thinking about past changes in cosmic ray flux. The rocks, ice, sediments, and crusts of Earth can act in a very quiet way like notebooks, though the handwriting is faint and often hard to interpret. Radiation can also affect chemistry in an atmosphere. Energetic particles entering an atmosphere can ionize molecules, break chemical bonds, and trigger chains of reactions. On Earth, the atmosphere is thick and chemically active, with oxygen, nitrogen, water vapor, ozone, and many other ingredients participating in complex cycles. Very large radiation changes could, in principle, affect ozone chemistry or increase radiation dose at high altitudes. But here we have to be careful. Earth is not a fragile soap bubble waiting for one cosmic ray to ruin the afternoon. It has thick atmospheric shielding, a magnetic field, oceans, geology, and biology that have endured many natural changes. The effects of interstellar cloud encounters would depend on the cloud, the duration of the encounter, the Sun's activity, Earth's magnetic field at the time, and many other conditions. Science does not support turning every interstellar change into a simple disaster story. Other planets would respond differently. Mars, for example, has a very thin atmosphere today and no global magnetic field like Earth's. It is much more exposed to solar and cosmic radiation at the surface. If the heliosphere changed, the space radiation environment around Mars would matter for future astronauts, surface chemistry, and the long-term processing of materials. The Moon, with no thick atmosphere and no global magnetic shield, is also directly exposed to space radiation. That is one reason lunar soil records solar wind particles and cosmic ray effects. The surfaces of airless bodies are, in a sense, long exposure plates facing space. They keep quiet records of particles that planets like Earth mostly absorb and hide. The giant planets have strong magnetic fields, especially Jupiter, whose magnetosphere is enormous. But their radiation environments are already intense because of trapped particles, moons, plasma sources, and magnetic fields. Interstellar weather would not affect them in the same way it affects Earth. It would first change the larger heliospheric conditions, which then influence the cosmic rays arriving throughout the solar system. Each planet has its own local defences and hazards. Saturn has a magnetosphere. Uranus and Neptune have tilted, unusual magnetic fields. Venus has a thick atmosphere but no Earth-like global magnetic field. Mercury has a weak magnetic field and little atmosphere. There is no single answer for what increased cosmic radiation would mean for the planets as a group. Each world is its own little negotiation between space and shelter. For life, the story becomes even more delicate. Life on Earth developed beneath the protection of the atmosphere, the magnetosphere, and the heliosphere. But life also developed in a universe where radiation is never zero. Natural background radiation has always been part of Earth's environment. Some radiation can damage DNA. Some mutations are harmful. Some mutations, over evolutionary time, become part of the variation on which natural selection works. That does not mean radiation is good in a simple sense. It means life has always existed in a balance with physical conditions, including radiation, chemistry, temperature, water, and planetary stability. If interstellar weather changed the cosmic ray environment, it could become one factor among many that shape biological and atmospheric history. But it would rarely be the only factor. There have been suggestions over the years that cosmic rays could influence climate by affecting cloud formation in Earth's atmosphere. This idea has been studied and debated, and it is not something to present as settled in a simple way. Earth's climate is driven by many strong factors: sunlight, greenhouse gases, ocean circulation, volcanic activity, orbital cycles, ice cover, and feedbacks between air, land, and water. Cosmic rays may have subtle atmospheric effects, but linking them directly to major climate changes is complex and uncertain. A calm way to say it is this: changes in cosmic ray flux could leave measurable traces and may have atmospheric consequences under some conditions, but Earth's climate system is far too complicated for a single neat cosmic explanation. The universe is rarely that cooperative. What is clearer is that heliospheric conditions affect radiation in space. Astronauts travelling beyond Earth's magnetic field face exposure to galactic cosmic rays and solar energetic particles. Space agencies care deeply about this because long-duration missions to the Moon, Mars, or beyond require better understanding of radiation hazards. The heliosphere's modulation of cosmic rays is part of the background environment for human exploration. When solar activity is high, galactic cosmic rays are more reduced, but solar storms can be more frequent and dangerous. When solar activity is low, there may be fewer solar storms but more galactic cosmic rays entering. It is a cosmic version of choosing between two imperfect umbrellas. Interstellar weather adds another slow layer to that. If the Sun's surrounding medium changed enough to alter the heliosphere, the background radiation environment for spacecraft and explorers could change too. This would not happen overnight in the current local cloud, but over long times and different galactic regions, it matters. A civilization planning across thousands or millions of years would care about the sun's path through the interstellar medium in a way we mostly do not need to for daily life. That is a strange thought. Future beings, if they exist, might one day include local interstellar conditions in their space weather forecasts, not because they are nervous, but because they are precise. For planets around other stars, this subject becomes even broader. The sun's heliosphere is only one example of an astrosphere, a bubble created by a star's wind as it moves through the interstellar medium. Other stars have different winds. Some are stronger, some are weaker. Young stars can be very active. Red dwarfs can flare intensely. Massive stars blow powerful winds but live short lives. A planet's radiation environment depends not only on its distance from the star, but also on the star's activity, the planet's magnetic field and atmosphere, and the surrounding interstellar medium. When scientists think about habitability beyond our solar system, they increasingly think in layers. A planet is not just a rock in the right temperature zone, it is part of a star system, and that star system is moving through a galaxy. This is one reason our own heliosphere is so important to study. It gives us the nearest example of how a star carves out a protective bubble, and how that bubble interacts with interstellar material. By understanding the sun's bubble, we learn how other stars may shelter or expose their planets. We cannot send voyagers to every nearby star, at least not yet, and certainly not before bedtime. But the physics we learn here can be applied elsewhere. The local interstellar cloud becomes a natural laboratory, not because it is extreme, but because it is close enough for us to measure. The phrase interstellar weather also includes dust. Interstellar dust grains can enter the solar system depending on their size, charge, and the filtering effects of the heliosphere and solar magnetic field. These grains are tiny, but they matter scientifically because they carry information about material outside the heliosphere. On airless bodies, dust and radiation slowly process surfaces, darkening, altering, and weathering them over long periods. This space weathering is strongest from local solar and micrometeoroid effects, but galactic cosmic rays and interstellar particles are part of the larger radiation and particle environment. Again, it is not dramatic in a movie sense, it is patient. Space changes surfaces by very small effects repeated for very long times. Comets and icy bodies in the outer solar system also carry records of exposure. The surfaces of objects far from the sun can be altered by cosmic rays over millions or billions of years. Radiation can change chemistry, create complex molecules, darken ices, and form crusts. When a comet later falls inward toward the sun, heating can reveal or erase parts of that history, so the wider radiation environment of the heliosphere and beyond is not only a hazard, it is a sculptor of materials. It writes slowly into ice and dust. For Earth's life, perhaps the most important lesson is not that interstellar weather controls everything, but that Earth's habitability is layered and relational. We're used to thinking of life as depending on sunlight and water, which it certainly does. But it also depends on planetary mass, atmosphere, magnetic history, geology, chemistry, orbit, the sun's long-term stability, and the protective structure of the solar system. The heliosphere is part of that larger habitability picture. It is not as immediate as the atmosphere, not as visible as clouds, not as familiar as seasons, but it belongs to the chain of conditions that make the surface of Earth so different from open space. That chain is not perfect. Earth has endured asteroid impacts, volcanic upheavals, ice ages, changes in atmospheric composition, solar variation, magnetic field reversals, and biological transformations. Life has been challenged again and again, but it has persisted, adapted, retreated, expanded, and changed. If interstellar conditions shifted the cosmic ray environment at certain times, Life would have met that too as one more pressure in a long history of pressures. It is tempting to look for one cause behind every change in Earth's past, but Earth is a complicated planet living in a complicated solar system inside a complicated galaxy. That complexity is not a problem, it is the story. The current Local Interstellar Cloud is part of a mild present chapter of that story. The Sun's bubble is large. Earth is protected by strong local shielding. The cloud outside is thin and warm. The cosmic rays that reach Earth are modulated by the heliosphere and then filtered by Earth's own defences. Life continues beneath an atmosphere that turns the harshness of space into blue sky. That blue sky is not just pretty, it is protection made visible. Every gentle daytime cloud above us exists below layers of shielding that reach from the air around Earth all the way out to the Sun's boundary with the galaxy. There is comfort in knowing this, but also perspective. We are not separate from interstellar space. We are sheltered within it. The solar system moves through the local interstellar cloud, and that cloud helps shape the heliosphere. The heliosphere helps shape the radiation environment around the planets. Earth's magnetic field and atmosphere shape what reaches the ground. Life grows inside the final layer, often unaware of the quiet negotiations happening far beyond Neptune. A tree does not need to know about the heliopause to grow leaves. A sleeping bird does not need to understand cosmic rays to rest on a branch. Yet both exist inside the protection of a star moving through a galaxy. If the Sun one day enters a denser cloud, or leaves the present local cloud complex, the heliosphere may adjust. The cosmic ray environment may shift. Instruments will notice long before human senses do. Future scientists may compare isotope records, spacecraft data, and models of the interstellar medium. They may trace how the Sun's surroundings changed across deep time. They may find that some passages left measurable marks and others passed almost unnoticed. That is the kind of science that asks for patience, because the galaxy does not change its local weather on our preferred schedule. For now, we can think of interstellar weather as the background condition beyond the Sun's bubble. Subtle, but real. It does not decide every fate. It does not reach directly into our rooms. It does not make the ocean tides or set the seasons. But it shapes the outer shield of the solar system, and through that shield it helps define the radiation environment in which planets live. It is one more reminder that habitability is not only a local feature, it is cosmic context made gentle enough for biology. Now the final view is wider and quieter. A moving solar system, a protected Earth, a galaxy full of changing environments, and a home that feels still only because the motion carrying it is so smooth, so old, and so much larger than our ordinary sense of place. This is one of the gentlest surprises in astronomy. Nothing in your room needs to move for you to be travelling. The walls can stay where they are. The floor can feel perfectly steady. The evening can be calm, the blanket warm, the lamp soft, and yet the entire scene is being carried by Earth as it turns, by Earth as it orbits the Sun, by the Sun as it moves through the Milky Way, and by the heliosphere as it passes through the faint local material between stars. We are moving through the galaxy right now, not as a dramatic escape, not as a roaring voyage, but as part of the ordinary condition of being here. That is what the local interstellar cloud reveals first. It shows us that home is not still, it is moving, it is not sealed away from the galaxy, it is nested within it. The solar system is not a small bright island surrounded by perfect nothingness. It is a star system travelling through a thin, warm, partly ionized region of the interstellar medium, inside a larger cavity shaped by ancient stellar explosions. The cloud is too thin to see and too faint to feel, but it is real enough to shape the outer edge of the Sun's protective bubble. It is real enough for neutral atoms to drift inward. It is real enough for spacecraft to measure its influence. It is real enough to give our solar neighbourhood a kind of interstellar weather, quiet and slow, but not meaningless. And perhaps the most calming part is that all of this happens without disturbing the ordinary surface of life. Earth does not tremble because the heliosphere meets the local cloud. The oceans do not lift because interstellar helium drifts through the outer solar system. Trees do not need to understand the local bubble in order to grow leaves. A cat on a windowsill, should one be present and pretending not to listen, does not need to know that Voyager crossed the heliopause. Life continues at its own scale. Rain falls when local weather gathers. Morning comes because Earth turns. Seasons pass because Earth's axis tilts as we orbit the Sun. Meanwhile, far beyond the planets, the Sun's wind presses outward into the interstellar medium, and the galaxy presses softly back. This layered stillness is worth holding for a moment. You are on Earth, which has an atmosphere. Earth is surrounded by a magnetic field, a magnetosphere that helps guide and deflect charged particles. Earth orbits inside the solar wind, the stream of plasma flowing outward from the Sun. The solar wind fills the heliosphere, a bubble reaching far beyond Neptune. The heliosphere moves through the local interstellar cloud, or through the mixed local cloud material around it. That cloud sits inside the larger local bubble, a low-density region in the Milky Way. The Milky Way itself is a galaxy in motion among other galaxies. This is your address, if we write it all the way out. It is a little longer than a postcode, and harder to fit on an envelope, but it is true. The local interstellar cloud also changes the feeling of darkness between the stars. We often imagine space as a blank, and in many ways it is wonderfully empty. But not completely. The darkness contains hydrogen and helium atoms, some neutral, some ionized. It contains tiny grains of dust, made from material that may have passed through older stars. It contains magnetic fields too weak to notice in daily life, but strong enough across vast distances to shape the motion of charged particles. It contains radiation, cosmic rays, and the long influence of starlight. The space between stars is not crowded like air, but it has a texture. It has conditions. It has a past. That past reaches far beyond our current Sun. The local bubble, the larger cavity around our stellar neighbourhood, was probably carved by multiple supernovae over millions of years. Massive stars lived, shone, pushed on the surrounding gas, and died. Their explosions cleared and heated space, swept material into shells, and helped sculpt the region through which the Sun now moves. Our present calm is, in a way, the old echo of those violent events. The stars that made the hollow are gone, but the hollow remains. The Sun travels through it with its planets, and Earth carries life through a region of the galaxy shaped by stars that disappeared long before anyone could give them names. There is a strange comfort in that, if we let it arrive gently. The universe is not tidy, but it is connected. The cloud outside the heliosphere is connected to the local bubble. The local bubble is connected to the lives and deaths of massive stars. The particles reaching the edge of the solar system are connected to older galactic processes. The atoms in your own body are connected to stellar history too, because the heavier elements that make planets and people were forged and scattered by earlier generations of stars. We are not merely looking out at the galaxy. We are made from it, moving through it, sheltered by one of its stars and surrounded by its thin remaining gases. The heliosphere gives this story a protective centre. The Sun is not only a light in the sky, it is a builder of boundaries. Its solar wind flows outward and creates a vast bubble around the planets. That bubble does not make us invincible, and it does not erase all cosmic radiation, but it helps reduce the galactic particles entering the inner solar system. Earth has its own defences too, with the magnetosphere and atmosphere doing work much closer to home. Together these layers help turn a harsh universe into a place where oceans can remain liquid, where air can be breathed, where nights can be quiet, and where a person can lie down and think about interstellar clouds without needing to worry about one drifting through the bedroom. Voyager made that boundary real in a new way. Before Voyager, the heliopause was a concept supported by theory and indirect evidence. After Voyager 1 crossed it in 2012 and Voyager 2 followed in 2018, the boundary became something humanity had touched with instruments. Not a wall, Not a glowing shell, but a shift in particles and fields. The old spacecraft moved from the region dominated by the solar wind into the region where the local interstellar medium takes over. They gave us direct measurements from beyond the sun's bubble, which is the sort of achievement that can feel almost too quiet for how remarkable it is. No fireworks marked the crossing, no human eye saw the edge. A machine built decades earlier simply reported that the environment had changed. IBEX gave us another kind of sight. It stayed much closer to Earth but mapped the edge of the heliosphere by catching energetic neutral atoms from the distant boundary. That is a wonderfully indirect way of seeing, like learning the shape of a distant coastline by catching grains of spray that have travelled across the night. IBEX revealed that the boundary has structure, including the unexpected ribbon of energetic neutral atoms. That ribbon told scientists that the interstellar magnetic field outside the heliosphere matters deeply. The sun shapes the bubble from within, but the galaxy shapes it from without. Home, even at the scale of the solar system, is a negotiation, and this may be the heart of the whole journey. Home is not a closed box, it is a relationship. Earth is home because it has the right mixture of rock, water, air, sunlight, chemistry, and time. The solar system is home because the sun holds its planets together and fills their space with light and wind. The heliosphere is home because it wraps the planets in the sun's extended influence. The local interstellar cloud is part of home because it is the surrounding environment our solar bubble is moving through now. The local bubble is part of home because it is the larger galactic hollow containing our neighbourhood. Every layer shapes the next. Every boundary is also a meeting place. This does not make Earth feel less special. If anything, it makes Earth feel more carefully placed within the great machinery of nature. Not special in the sense that the galaxy arranged itself for us, with little arrows pointing toward our planet and a welcome sign near the moon. The universe does not seem to work that way, and it would be a bit much to ask. But special in the sense that Earth is a rare and delicate result of many conditions overlapping. A stable star, a planet at the right distance, a thick atmosphere, a magnetic field, liquid water, chemistry rich enough for life, a large enough moon to help steady the planet's tilt, a heliosphere surrounding the whole planetary system, a current local interstellar environment that is thin enough for the sun's bubble to remain vast. Each of these pieces belongs to a different scale, and together they make our familiar world possible. The local interstellar cloud also teaches patience. It changes slowly by human standards. The sun may be near a boundary between local cloud materials or inside a mixed region, but any transition unfolds over thousands of years or more. We're used to fast news, fast messages, fast lights, fast weather, fast worries. The interstellar medium is not in a hurry. It moves with the galaxy's long timing. Its cloud edges are soft, its atoms are sparse, its influence is subtle. It reminds us that not everything important announces itself quickly. Some of the deepest conditions of home are slow enough to be invisible. That slowness can be soothing. Tonight, while you rest, the solar system continues its motion through the local cloud. The sun does not need your attention to keep producing the solar wind. The heliosphere does not need to be watched in order to hold its shape. Voyager continues outward in the dark. IBEX and other instruments continue to help scientists understand the boundary. Earth continues to turn. The atmosphere continues to press gently around us. Gravity continues to hold you to the surface. You're travelling through interstellar space, in one sense, and yet you're also simply here, breathing under a familiar sky. There is a lovely contradiction in that. We're moving at astonishing speeds, but we feel still. We are inside a galaxy, but we live in rooms and streets and fields. We are exposed to the universe, but also protected from it. We are tiny compared with the local bubble, and yet we are large enough in curiosity to map it. We are brief compared with the sun's journey, and yet we can understand that journey. We are made of atoms shaped by ancient stars, and we use those atoms to build instruments that detect other atoms drifting in from interstellar space. The universe is vast, but it is not beyond connection. Perhaps this is why the question of what the solar system is moving through feels so different from simply asking where it is. A location can sound fixed. A motion tells a story. The Sun is not merely located in the Milky Way, it is travelling through it. The heliosphere is not merely a bubble, it is being made continuously by the solar wind and reshaped continuously by its surroundings. The Local Interstellar Cloud is not merely a named patch of gas, it is the current medium through which our star's outer influence is passing. Home is not a dot, it is a journey with layers, and yet, from the human point of view, nothing about this journey takes away the softness of the present moment. You can still listen to the quiet. You can still notice your own breathing. You can still imagine the Earth turning slowly beneath the night. Above the atmosphere, charged particles follow magnetic fields. Farther out, the solar wind streams past the planets. Far beyond Neptune, that wind slows and thickens in the heliosheath. At the heliopause, the Sun's influence yields to interstellar space. Outside, the Local Interstellar Cloud drifts and flows, thin as almost nothing, yet real. Beyond that, the local bubble opens around our stellar neighbourhood, a vast cavity left by ancient stars. And beyond that, the Milky Way carries everything in its great slow rotation. So what does our journey through the local cloud reveal about home? It reveals that home is bigger than we usually imagine. It includes the ground beneath us, yes, and the atmosphere above us, and the sun that warms us. But it also includes invisible protections and distant boundaries. It includes particles from the sun and atoms from between the stars. It includes old supernovae, magnetic fields, and the faint pressure of gas so thin it would seem like emptiness to our hands. It includes motion we do not feel, and distances we cannot cross in a human lifetime. Home is not only the place that feels familiar, it is the whole layered system that allows familiarity to exist. It also reveals that being small is not the same as being separate. We are tiny compared with the heliosphere. The heliosphere is tiny compared with the local bubble. The local bubble is tiny compared with the Milky Way, and the Milky Way is only one galaxy among many. But the smallest layer is still connected to the largest. A change in the sun changes space weather near Earth. A change in the surrounding interstellar medium can reshape the heliosphere. Ancient supernovae can carve the local cavity through which the sun later moves. The universe is not a collection of isolated objects. It is a set of relationships, some bright, some invisible, some fast, some slow. And now, as this quiet journey comes to rest, or at least to the kind of rest possible on a planet moving through a galaxy, we can return to where we began. Where are you listening from tonight? What time is it where you are? Perhaps the room is dark now. Perhaps the day is just beginning. Perhaps you are somewhere under city lights, or near open fields, or in a place where the sky is hidden by clouds. Whatever your local weather may be, the larger weather continues far beyond it. Earth turns, the sun moves, the heliosphere presses gently through interstellar gas. The solar system keeps travelling through the local interstellar cloud, or its nearby mixed edge, without asking us to feel the motion. If this journey through the invisible neighbourhood around the sun has brought you a little calm, or made the universe feel both larger and more companionable, I would be ever so grateful if you liked the video, subscribed, or shared this quiet corner with someone else who might enjoy drifting through science before sleep. It helps these gentle journeys keep travelling too, in their own small way, from one tired mind to another. For now, let the scale soften rather than overwhelm you. You do not need to hold every distance in your head. You do not need to picture every atom outside the heliopause. It is enough to know that you are here, inside layer after layer of shelter, carried by a star through a faint cloud between stars. The solar system is moving, but it is moving gently. The galaxy is vast, but tonight it can be quiet. And somewhere beyond the planets, beyond the cold outer dark, the sun's protective bubble meets the thin breath of interstellar space, while Earth turns slowly beneath you, offering the simple gift of rest. Sleep well, fellow traveller, wherever you are in this moving home, and wherever the local interstellar cloud is carrying us next.